The universe is as beautiful as it is terrifying, a vast expanse dotted with regions that defy comprehension and push the limits of known physics. From Blazar jets, shooting streams of energy capable of vaporizing anything in their path, to the surfaces of Quark Stars, where gravity crushes matter into its most fundamental state, these are places where life, no matter how advanced, could never hope to survive. However, these aren't just the deadliest places in the universe, they're also the most fascinating, pushing the boundaries of what we thought we knew about space and time. Pulsar wind nebulae. The space surrounding pulsars is among the most hostile environments known. At the heart of these zones lies a rapidly spinning neutron star, emitting winds of high-energy particles traveling near the speed of light. These pulsar winds create nebulae that glow intensely in X-rays and gamma rays, making them some of the brightest and deadliest phenomena in the universe. These nebulae are powered by the pulsar's rotational energy. As the pulsar spins, its immense magnetic fields twist and accelerate charged particles into relativistic speeds. This acceleration process releases energy in the form of synchrotron radiation, illuminating the nebula with a spectrum of high-energy emissions. The particles themselves, traveling close to light speed, carry energy that can obliterate anything nearby. Around these pulsars, the nebula expands into magnetized cavities. These are not empty voids, but zones filled with plasma and magnetic turbulence. As the pulsar ejects its wind, it forms a boundary known as the termination shock. Here, the particles abruptly decelerate, transferring their energy to the nebula and generating powerful shock waves. These shocks can influence nearby matter, stripping atoms of electrons and disrupting molecular structures. At larger scales, the nebula interacts with the interstellar medium. The resulting bow shocks created by pulsars moving at high speeds through space compress and heat interstellar gas. These shocks form distinctive arcs and bubbles that extend for light years, reshaping the surrounding environment. The interplay of these forces often makes pulsar wind nebulae appear asymmetric, with their shapes distorted by local conditions. The Crab Nebula, which is propelled by the Crab Pulsar, is a famous example. Extending from its poles, this nebula displays complex formations made of filaments and rings. These characteristics are seen in several pulsar wind nebulae around the galaxy and are not exclusive to the Crab Nebula. The ever-changing character of the winds and the harsh conditions they generate are shown by these buildings. The magnetic fields within these nebulae are not stable. They twist, reconnect, and unleash bursts of energy, accelerating particles even further. This process, known as magnetic reconnection, is responsible for some of the most intense and unpredictable energy releases in space. These events produce gamma-ray flares that can be detected across the galaxy. Cosmic ray research also makes use of pulsar wind nebulae. Theoretically, pulsar activity has a major impact on these high-energy particles that originate from different astrophysical events. Particles that manage to break off of the nebula become cosmic rays, which enrich the Milky Way's high-energy environment. Along with the nebula's inherent energy, the pulsar is an unstoppable force in its own right. Particles are propelled to unprecedented speeds by the electric fields produced by the pulsar, which spins at hundreds of times every second. The pulsar gradually dims and changes the shape and brightness of the nebula as it loses energy. Despite these transformations, the nebula is still a powerful accelerator of particles and a source of radiation. The impact of these nebulae extends far beyond their immediate surroundings. They are among the brightest gamma-ray sources in the Milky Way, outshining entire regions of the galaxy. These emissions are not random, but show patterns and structures that provide clues about the pulsar's behavior and the surrounding environment. For example, polarized radiation from these nebulae reveals the alignment of magnetic fields, offering insights into their internal dynamics. The interaction between the nebula and the interstellar medium is another area of intrigue. As the nebula expands, it collides with surrounding gas and dust, creating turbulence and compressing material. This process can sterilize nearby molecular clouds, halting star formation, and reshaping the interstellar landscape. Such interactions highlight the destructive yet transformative role of pulsar wind nebulae in galactic ecosystems. Some pulsar wind nebulae are accompanied by relativistic jets, narrow streams of particles moving close to the speed of light. These jets, often aligned with the pulsar's poles, cut through space with immense energy, creating trails of radiation and influencing nearby matter. These jets add another layer of complexity to the already chaotic environments of these nebulae. In rare cases, pulsars exist in binary systems where the pulsar's wind interacts with its companion star. These interactions produce unique nebulae with features distinct from isolated systems. The combined winds of the pulsar and its companion create turbulent zones of high-energy radiation and particle acceleration, extending the reach of the nebula's deadly influence. As pulsar wind nebulae age, they evolve. Initially bright and compact, they expand and fade over tens of thousands of years. However, even in their dimmer stages, they remain significant contributors to the cosmic environment. Their residual energy continues to shape the interstellar medium, leaving a lasting imprint on their surroundings. Supernova remnants and pulsar wind nebulae are interrelated, which is an additional important consideration. The presence of supernova remnants within several pulsar wind nebulae further complicates their structure. Shock fronts and turbulence are produced by the interaction of the expanding supernova material with the pulsar wind, which enhances the nebula's energy production and changes its appearance. Observations across multiple wavelengths are crucial for understanding these phenomena. While X-rays and gamma rays reveal the high-energy emissions, radio and infrared observations provide insights into the cooler, denser regions of the nebula. These multi-wavelength studies allow astronomers to piece together a comprehensive picture of the processes at work. Pulsar wind nebulae are not always located inside our galaxy. Examples from other galaxies have been found, which have the same characteristics but on a grander scale. These faraway nebulae demonstrate how these dangerous areas are affected by processes that are common to the whole cosmos. Despite their destructive nature, pulsar wind nebulae are also sources of wonder. Their intricate structures, intense radiation, and dynamic interactions make them some of the most fascinating objects in the cosmos. Hypernova remnants. Pulsar wind nebulae push the limits of extreme environments, creating zones where particles move at nearly the speed of light. The radiation here isn't just intense, it's lethal, streaming outward in waves of high-energy electrons and positrons. These winds carve out cavities in the interstellar medium, transforming their surroundings into regions of relentless particle acceleration. Structures that vibrate with energy are formed within these zones by twisting and compressing magnetic fields. Up close, these zones are anything but lovely, yet from Earth, they seem as unmistakable luminous tendrils caused by the interaction of radiation and magnetic instability. Planets in the vicinity, if any, would have their atmospheres rapidly stripped away by the ferocity of the storms. The remnants of hypernovae take this destruction to an entirely different level. When a massive star collapses, the energy released can outshine entire galaxies for brief moments. Gamma-ray bursts are often born here, and their narrow jets of radiation are among the most dangerous phenomena in the cosmos. These bursts have the power to sterilize planets across vast distances, wiping out life long before it could adapt. The shockwaves from these explosions heat surrounding gas to millions of degrees, creating expanding shells of deadly X-rays and gamma rays. Even areas far from the hypernova's epicenter aren't safe. The remnants scatter cosmic dust and high-energy particles, leaving behind an interstellar minefield for anything passing through. In regions of young star systems, planetesimal collision fields reveal the chaotic beginnings of planetary formation. These areas are dense with small rocky bodies that collide at incredible speeds, creating debris storms that sweep through space. These collisions not only shape the early architecture of star systems, but also pose a constant threat to any developing planetary environments. Additional mystery surrounds stripped galactic centers. The gas and stars have been sucked out of these galaxies, leaving behind just their dense centers. These areas are characterized by severe radiation zones and gravitational traps caused by exposed black holes and compact star clusters. Cosmological interactions may consume and change galaxies, as the bare cores are a sobering reminder of. Star-forming regions also hold their share of danger, particularly the birthplaces of supermassive stars. The ultraviolet radiation and shock waves produced here obliterate anything within proximity. The process of star formation in these regions is not gentle. It's a violent, high-energy spectacle that reshapes its environment entirely. The magnitude of cosmic violence is shown even on a galactic scale by shock fronts caused by galaxy cluster collisions. Galactic collisions produce tremendous shock waves, which in turn heat gas to millions of degrees and release powerful X-rays. Shock fronts are among the most intense cosmic phenomena because they may wipe out anything within millions of light years. There is also a great deal of curiosity about cosmic string wakes, should they really exist. The gravitational forces of these hypothetical cosmic string trails are so powerful that they might deform space-time and stuff in their vicinity. Anything in the area may have its dynamics drastically changed if the wakes generated areas of very high density and curvature. Even white dwarfs contribute to this deadly catalogue through helium flash zones. These regions of explosive helium fusion create localized thermonuclear detonations that release enormous amounts of energy. While brief, these events can have lasting impacts on their immediate surroundings. Planets themselves can harbor extreme conditions, as seen in those with extraordinarily strong magnetospheres. These magnetic fields trap high-energy particles, creating radiation belts that would make survival on or near such planets impossible. Big molecular cloud fragmentation zones show how powerful gravitational instability is. Intense bursts of star formation are set off by the abrupt collapse of these concentrated areas of cold gas. On the other hand, these zones' turbulence and shock waves pose risks to the surrounding area and add to the continuous cycle of stellar development. These occurrences serve as reminders of the universe's enormous destructive and creative power, highlighting its enormous and frequently hostile beauty. Blazar jet impact zones. The immense power unleashed by blazar jets begins at the heart of supermassive black holes. As material spirals into the black hole's accretion disk, immense energy is generated through magnetic reconnection near the event horizon. These magnetic fields twist and anchor themselves to the spinning black hole, launching streams of particles outward at speeds nearing that of light. These relativistic jets carry lethal energy across intergalactic distances, making them among the most dangerous cosmic phenomena. The orientation of these jets is critical. When aligned directly with Earth, their emissions are amplified due to relativistic beaming. This creates a bright beacon that outshines entire galaxies. The energy emitted in these jets is incomprehensible, with a single jet producing more power than millions of stars combined. What makes them particularly hazardous is the high-energy gamma rays produced as particles within the jets interact and accelerate. These gamma rays can sterilize any planets or systems unfortunate enough to be in the jet's path. Blazar jets are not static. Internal collisions within the jets, caused by variations in particle speeds, create shock fronts. These shocks are regions of intense activity where particles are further accelerated, emitting bursts of gamma rays and X-rays. These flares are often detected as sudden increases in brightness, providing glimpses into the dynamic processes at work. The magnetic fields within the jets, while maintaining their collimation, are also turbulent, fueling the chaotic acceleration of particles. The impact of these jets extends far beyond their immediate path. As they collide with the surrounding intergalactic medium, they create vast cavities and hotspots. These regions are filled with high-energy plasma, glowing brightly in X-rays and radio waves. The jets also carve channels through intergalactic gas, redistributing material and shaping the evolution of nearby galaxies. By suppressing star formation in their vicinity, Blazar jets regulate the growth and structure of galaxies, effectively acting as cosmic architects. At their termination points, where the jets lose momentum, they create brilliant hotspots known as lobes. These lobes are reservoirs of energy, filled with charged particles and magnetic fields that emit radio waves detectable across billions of light years. The power of these jets is so immense that they can persist for millions of years, continuously influencing their surroundings. Blazar jets are also prolific sources of ultra-high energy cosmic rays. These particles, traveling at nearly the speed of light, carry energies that challenge our understanding of physics. They bombard Earth from all directions, offering clues about the processes occurring deep within these jets. Additionally, neutrinos, elusive particles generated by interactions within the jets, provide further insight. These neutrinos are nearly impossible to detect, but hold key information about the extreme environments near supermassive black holes. The Blazar jet's remarkable diversity stands out among its most notable characteristics. Their luminosity can fluctuate on periods from hours to months, denoting dynamic changes in the interior circumstances of the jets. This fluctuation is associated with accretion disk and magnetic field instability, which periodically interrupts the black hole's material input flow. Radiation bursts visible from Earth are produced when these disturbances drive shockwaves along the jet. The extent of these jets is staggering. They can stretch for hundreds of thousands of light years, bridging the space between galaxies and impacting vast regions of intergalactic space. Along their path, they interact with the cosmic microwave background radiation, producing secondary gamma rays that add to their lethal output. These interactions highlight the interconnectedness of cosmic structures, where even the faintest background radiation plays a role in shaping the universe. The alignment of a Blazar jet with Earth's line of sight is a matter of chance, but it has profound implications for how we observe them. When directly aligned, the energy we perceive is magnified, making these jets some of the brightest objects in the universe. This alignment also makes them invaluable for studying the extreme physics of black holes and relativistic particle acceleration. Even though Blazar jets are quite powerful, scientists still don't agree on what makes them up. Do protons play a major role, or do electrons and positrons predominate? The answer to this question may provide light on the activities taking on at the source of these jets and the mechanisms that propel them. In order to solve these puzzles, observations at many wavelengths, ranging from radio to gamma rays, are required. The regions surrounding Blazar jets are not barren. Interactions with dense gas clouds can lead to the fragmentation of the jets, spreading their energy over larger areas. This process contributes to the enrichment of intergalactic gas with heavy elements, influencing the chemical composition of future star-forming regions. The jets also redirect gas flows, creating streams and filaments that feed star formation in distant parts of the universe. One way to investigate extreme physics is by observing Blazar jets, which are like little nature labs. This is a once-in-a-lifetime chance to put ideas of particle acceleration and magnetohydrodynamics to the test, since the energy involved are beyond anything that can be achieved on Earth. Additionally, they shed light on how supermassive black holes, the central mass of the vast majority of galaxies, have developed and changed throughout time. The influence of Blazar jets extends to the cosmic web itself. By injecting energy into the intergalactic medium, they contribute to the large-scale structure of the universe. The cavities and shock waves created by these jets shape the distribution of matter, connecting galaxies and clusters through networks of hot gas and plasma. Blazar jets are also a testament to the interconnectedness of cosmic phenomena. Their emissions are influenced by the rotation of the black hole, the magnetic fields threading the accretion disk, and the properties of the surrounding intergalactic medium. This interplay of factors creates a system that is both chaotic and ordered, a delicate balance that sustains these jets for millions of years. In studying Blazar jets, scientists uncover not only the secrets of black holes, but also the forces that shape the universe. These jets are reminders of the immense power and complexity of the cosmos, where the interplay of energy and matter creates structures on scales beyond human comprehension. They are among the deadliest places in the universe, yet they hold the key to understanding some of its most fundamental processes. Rayt star winds. When Pulsar wind nebulae unleash their radiation storms, they test the limits of what can be survived. We discover locations where the energy surpasses even the explosive output of normal supernovae as we get into Hypernova Remnants. However, the tale of cosmic energy's brutality is far from over. After Rayt stars, the natural world creates settings so hostile and unpredictable that staying alive is an impossibility. These stars are enormous, unstable, and ephemeral. They have a short lifespan and then explode in a cosmic explosion. In their final stages, Rayt stars eject material into space at unimaginable speeds. These stellar winds aren't gentle breezes. They move at thousands of kilometers per second, carrying high-energy radiation and heavy elements. Any nearby planet would be stripped of its atmosphere in moments, leaving nothing to shield its surface from deadly radiation. The winds would erode even the planet's crust, scattering particles into space. What's left is a barren remnant, unable to sustain life or even retain its original shape. The impact of these winds is visible in the formation of cosmic bubbles. These vast cavities of hot plasma are carved out of the interstellar medium, leaving a wake of destruction that alters the surrounding environment. These bubbles act like cosmic fingerprints, showing the chaotic influence of Rayt stars over great distances. The carved-out regions are often surrounded by shockwaves of gas and dust, remnants of material blasted away by the star's immense power. If two Rayt stars exist in a binary system, the chaos escalates. Their winds collide, generating massive shockwaves that heat the gas to extreme temperatures. These interactions create bursts of X-rays and gamma rays, lethal to any nearby life and hazardous to even distant regions. This phenomenon creates an environment so hostile that it disrupts the formation of new stars or planets. The radiation and particle density simply overwhelm the conditions necessary for calm, stable growth. These stars are also prolific sources of heavy elements like carbon, nitrogen, and oxygen, enriching their surroundings but simultaneously creating turbulence in nearby molecular clouds. While this enrichment contributes to the eventual formation of new stars, it does so at the cost of immense instability. The turbulence can delay star formation for millions of years, setting off a chain reaction of destruction and delayed creation. Perhaps the most stunning feature of Rayt stars is their ability to accelerate particles to near-light speeds. These high-energy particles, known as cosmic rays, bombard surrounding regions with radiation. These rays penetrate deep into gas clouds, destroying molecular bonds and ionizing particles. They alter the chemistry of their surroundings, often making regions inhospitable to the development of complex molecules needed for life. The radiation pressure from these stars is another critical factor in their lethality. As the star emits light, the photons push against nearby material, creating a force strong enough to eject matter far into space. This constant shedding of mass alters the star's gravitational field, destabilizing the orbits of any nearby objects. Planets, asteroids, or even smaller stars can be thrown off course, sent spiraling into chaos, or entirely ejected from their systems. Rayt stars don't just influence their immediate surroundings. Their reach extends across galaxies. Their powerful winds and radiation contribute to galactic recycling, a process where material from old stars feeds into the creation of new ones. But this recycling comes at a cost. The regions around these stars become fragmented, filled with dense pockets of material that are prone to collapse. These collapses generate additional shockwaves and further destabilize the already volatile environment. The nebulae are thick gas and dust clouds that are frequently lit by the star's powerful radiation. They are both aesthetically beautiful and extremely hazardous. Any organic stuff can be destroyed by the radiation levels within these nebulae, leaving only the most robust particles remaining. Within these zones, stable systems cannot develop due to the continual stream of high-energy particles. When these stars are part of a galactic cluster, their influence compounds. The combined winds from multiple Wolf-Rayet stars can create massive cavities within the cluster, affecting the orbits and stability of other stars. These cavities act like gravitational traps, altering the flow of material within the cluster and leading to the formation of chaotic, unstable regions. Even at the end of their lives, Wolf-Rayet stars continue to be agents of destruction. Many end in spectacular core collapse supernovae, sending out shockwaves that travel for millions of light-years. These explosions release massive amounts of energy, sterilizing entire regions of space. The intense radiation from these events can disrupt the magnetic fields of nearby systems, further adding to the chaos. Some Wolf-Rayet stars go to even greater extremes, merging with black holes as they collapse. Long gamma-ray bursts are a common visual representation of the intense energy jets produced by these occurrences. These explosions may sterilize areas far away from the star's initial position and are among the most intense events in the cosmos. A single burst's destructive power can be comparable to that of a galaxy, if not greater. Unpredictability is amplified by the fact that wind intensity might vary. Periods of heightened or diminished activity can cause these stars to change the strength of their winds and radiation. Because of this unpredictability, the environment is always evolving, going through phases of relative stability and then complete chaos in the space of a few years. This kind of uncertainty makes survival extremely difficult for any neighboring system. Wolf-Rayet stars also distort magnetic fields in their surroundings. The interaction of their winds with the star's magnetic field creates twisted, chaotic field lines that influence the behavior of charged particles. These distorted fields can trap particles, creating regions of intense radiation that further destabilize the surrounding environment. The study of polarized light from these stars provides additional insights into their influence. As their winds interact with surrounding dust clouds, they produce polarized light, which scientists can use to map the chaotic environment. This mapping reveals the extent of their impact, showing just how far-reaching their effects can be. The ultimate fate of many Wolf-Rayet stars is to become stellar mass black holes. As they collapse, they leave behind regions of intense gravitational pull and radiation. These remnants continue to influence their surroundings, drawing in material and emitting high-energy particles. Even in death, these stars remain deadly. Wolf-Rayet stars are among the most violent and influential objects in the universe. Their winds, radiation, and eventual collapse shape their surroundings in profound ways, leaving a legacy of destruction and instability. They are a testament to the raw power of the cosmos, reminding us of the delicate balance required for life and stability in such a hostile universe. From the Pulsar wind nebulae to the hypervelocity star paths, the story of deadly cosmic phenomena is interconnected. Each phenomenon, including the chaotic winds of Wolf-Rayet stars, contributes to a broader narrative of destruction, transformation, and the relentless forces that shape our universe. These stars are not isolated threats. Tidal disruption zones near black holes. The regions near Pulsar wind nebulae set the stage for understanding the relentless forces of the cosmos. High-energy particles, moving close to the speed of light, create storms of deadly radiation that obliterate anything unfortunate enough to wander into their vicinity. But if we think the aftermath of a pulsar is violent, the destruction found near tidal disruption zones surrounding black holes takes devastation to a completely different scale. When a star strays too close to a black hole, it faces an encounter that can stretch, compress, and ultimately disintegrate it into streams of gas and debris. This is the result of overwhelming tidal forces, with the black hole's gravity pulling much harder on one side of the star than the other. The result? A violent process astronomers call spaghettification. The stellar material, now in thin, elongated strands, doesn't simply disappear. It feeds the black hole in a catastrophic cascade. These torn remains often spiral toward the black hole, forming an accretion disk where temperatures can soar to millions of degrees. The accretion disk is not just a chaotic sea of shredded matter, it becomes a generator of extraordinary energy. As the material gets pulled inward, friction and gravitational forces heat it up to emit intense X-rays and ultraviolet light. These emissions can spread far beyond the black hole's immediate vicinity, creating a zone hostile to life on an unimaginable scale. Such energy output is so potent, it can sterilize regions of space, ionizing gas and disrupting the stability of nearby systems. Not all material from the disrupted star ends up in the black hole. Some of it is ejected into interstellar space at speeds exceeding tens of thousands of kilometers per second. These high-speed streams of stellar debris add to the chaos, colliding with other interstellar material and creating shockwaves that reverberate through the galaxy. These shockwaves aren't harmless. They compress and heat gas, triggering bursts of radiation that can further impact surrounding regions. One fascinating consequence of these events is the possibility of relativistic jets, narrow, high-speed streams of matter launched from the vicinity of the black hole. These jets, moving at speeds close to the speed of light, can extend for thousands of light years, piercing through the fabric of the galaxy. Anything in their direct path is subject to annihilation, as the energy carried by these jets can vaporize planets and strip atmospheres. The precise mechanisms driving these jets remain a topic of intense study, but magnetic fields around the black hole likely play a significant role in shaping and accelerating them. Tidal disruption zones are also unique cosmic laboratories for studying the behavior of extreme gravitational forces. As the star's material gets stretched and compressed, it emits specific types of radiation that give scientists clues about the mass, spin, and environment of the black hole involved. This radiation is not uniform. It varies depending on how the disrupted material interacts with the accretion disk, creating patterns that can last for weeks or even months. These events also shed light on the population of dormant or hidden black holes scattered across the universe. A black hole that might otherwise remain invisible suddenly reveals itself when it consumes a star, producing bursts of X-rays and gamma rays that astronomers can detect. These discoveries help map the distribution of black holes in various galactic environments, deepening our understanding of their role in shaping galaxies. While the destructive force of tidal disruption events is clear, their impact extends beyond destruction. Some of the stellar material ejected during these encounters doesn't vanish into the void. Instead, it can contribute to the enrichment of the interstellar medium, scattering elements formed in the star's core into surrounding space. This material, rich in elements like carbon, oxygen, and nitrogen, may eventually become part of new stars, planets, or even life. Thus, even in destruction, there is a strange cycle of renewal. The scale of energy conversion in these events is staggering. A tidal disruption event can release as much energy as a supernova, but over a much longer timescale. The gravitational forces near the black hole convert the kinetic and potential energy of the stellar debris into heat and light, with efficiency far surpassing what is possible in nuclear fusion. This high efficiency makes tidal disruption zones some of the brightest sources of energy in the universe, visible across vast cosmic distances. There is also the profound impact these events have on their host galaxies. The intense radiation and energy output from a tidal disruption event can heat and expel gas from the galaxy's core, suppressing star formation for millions of years. On a smaller scale, the shockwaves created by ejected material can compress nearby gas clouds, triggering bursts of star formation in surrounding regions. The interplay between destruction and creation makes these zones a crucial part of galactic evolution. The variability in tidal disruption events adds another layer of complexity. Depending on the size and type of the disrupted star, the black hole's mass, and the angle of the encounter, these events can produce dramatically different outcomes. For instance, smaller stars might be entirely consumed, while larger ones could lose only their outer layers, surviving the encounter but left unstable and stripped. Binary star systems add further unpredictability, as one star might be consumed while the other is ejected at incredible speeds, becoming a hypervelocity star. While tidal disruption zones represent some of the deadliest environments in the universe, they are not isolated phenomena. They often exist in dense galactic cores where interactions between stars, black holes, and interstellar gas are frequent. The presence of multiple black holes or dense stellar clusters can amplify the frequency of these events, creating regions of space where destruction is not an exception but a rule. These zones also play a role in the broader cosmic tapestry, influencing the behavior of gas flows across intergalactic space. Material expelled during tidal disruption events can travel vast distances, interacting with cosmic filaments and contributing to the large-scale structure of the universe. The gravitational waves generated during these encounters add another layer of connection, rippling through space-time and offering insights into the fabric of the cosmos itself. What stands out in tidal disruption zones is the interplay of extremes. Gravity, radiation, and motion combine to create phenomena that challenge our understanding of physics. From the microscopic scale of atomic interactions in the accretion disk to the cosmic scale of galaxy-wide impacts, these events encapsulate the universe's raw power. They are reminders of both the fragility of stars and the resilience of the cosmic cycle that continually rebuilds from the wreckage of destruction. In transitioning to other extreme regions, it's clear that tidal disruption zones are not isolated in their hostility. Nearby environments, such as those dominated by Pulsar wind nebulae or relativistic jets from Blazars, share the same disregard for anything crossing their paths. These areas are connected by the universe's unrelenting forces, gravity, radiation, and motion, demonstrating how the cosmos shapes and reshapes itself in the most dramatic ways. Each of these deadly locations is a piece of the puzzle, revealing more about the universe's dynamic and often violent nature. Quark star surfaces. Continuing from the extreme phenomena of Pulsar wind nebulae, the journey through the universe's deadliest realms leads us to a place where the boundaries of matter itself are tested. Quark stars, theoretical remnants of the densest neutron stars, are thought to push the laws of physics to their limits. Unlike neutron stars, which are composed of tightly packed neutrons, quark stars delve deeper into the building blocks of matter, breaking apart neutrons into their smallest components, quarks. The surface of a quark star is a battlefield of forces, where gravity is so intense that it compresses matter to densities unimaginable anywhere else. A teaspoon of this material could outweigh an entire mountain, and this sheer mass creates gravitational fields strong enough to disrupt time itself. For anything that dares to approach, the experience is catastrophic. Nearby objects are pulled apart by tidal forces, each atom stretched and torn before disintegrating completely. What sets quark stars apart is their surface, which might expose strange quark matter. This substance, unlike anything we encounter on Earth, may hold unique properties. One of the most dangerous is its potential to destabilize normal matter on contact, converting it into more strange quark matter in a process that releases vast amounts of energy. In theory, even a tiny piece of this material ejected from the star could wreak havoc if it collided with another celestial body. Surrounding these stars, radiation storms of gamma rays and X-rays flood space. The lack of a conventional atmosphere means that this radiation is not filtered or absorbed, but instead unleashed in its raw, deadly form. Gamma-ray bursts, which are among the most energetic events in the universe, might even have origins tied to quark stars. These bursts can sterilize entire star systems, erasing any potential for life. Yet the dangers of quark stars go beyond radiation and gravitational extremes. If a quark star interacts with a binary companion, it might draw matter from the companion star, forming an accretion disk of hot plasma. As this plasma spirals inward, it heats to temperatures that exceed those found in the cores of most stars, emitting blinding light and lethal radiation. This process, while incredibly destructive, provides clues about the nature of these enigmatic stars. Rotational dynamics of quark stars add another layer of complexity. Many of these stars might rotate at incredible speeds, with some completing a full rotation in milliseconds. This rapid spinning generates centrifugal forces capable of flinging particles into space at relativistic speeds. These ejected particles form powerful jets that travel vast distances, creating hazards far from the star itself. Magnetic fields around quark stars are another factor to consider. These fields can be trillions of times stronger than Earth's, shaping the behavior of nearby particles and even influencing the paths of photons. In regions where magnetic fields dominate, normal laws of motion and energy can seem almost suspended, as particles are accelerated and bent in unnatural ways. A quark star's immediate vicinity is a whirlwind of new and strange energies and particles. Any contact with regular matter triggers tremendous reactions due to the absence of electrons on the surface. This disordered space is where relativistic phenomena and quantum effects mix, producing theoretical but inherently hazardous circumstances. Gravitational waves from quark stars, especially in binary systems, might offer a way to detect them indirectly. When two such stars orbit each other or merge, they send ripples through spacetime that can be measured across galaxies. These waves not only confirm their presence, but also reveal details about their masses and compositions. Such events, though brief, release immense energy, affecting regions far from their origins. The possibility that quark stars have a role in molding the cosmos at large is another fascinating feature of these objects. Strange quark matter may have an effect on the distribution of dark matter, or perhaps contribute to the development of galaxy clusters, according to some experts. If this is so, quark stars are cosmic actors in a far bigger game than just local dangers. Theoretical predictions about the behavior of quark stars continue to evolve. Some suggest that their surfaces might act as superfluids, where particles move without resistance. This state would allow for rapid and efficient energy transfer, creating bursts of activity that are difficult to explain through other means. These bursts might account for some of the mysterious signals detected by astronomers, including fast radio bursts, whose origins remain largely unexplained. Proximity to a quark star amplifies its dangers. For any nearby planet or star, the combination of radiation, gravitational distortion, and particle ejections makes survival impossible. Even the strongest planetary magnetic fields would struggle to deflect the onslaught, leaving exposed surfaces to be stripped away layer by layer. The nature of quark stars, if they exist, challenges our understanding of matter and energy. They represent a state of existence where normal rules break down, where the smallest building blocks of the universe dictate the behavior of entire celestial bodies. This makes them not just deadly, but also scientifically fascinating. Yet their potential for destruction cannot be overstated. If a quark star were to form in our galaxy, its effects would be profound. The radiation alone could threaten life on Earth if the star were close enough. Moreover, the ejection of strangelets into our solar system could destabilize matter on a planetary scale, with outcomes that are almost impossible to predict. While quark stars remain largely hypothetical, the possibility of their existence adds another layer of complexity to the universe's deadliest places. Each aspect of their behavior, from their immense density to their violent energy releases, serves as a reminder of the extremes present in the cosmos. In the broader context of space, where everything from hypervelocity stars to cosmic string wakes challenges survival, quark stars stand out as unique hazards, blending theoretical physics with the raw power of the universe's most extreme environments. Cosmic microwave background cold spot. The exploration of the deadliest places in the universe naturally leads to the enigmatic cosmic microwave background cold spot. This vast anomaly in the relic radiation of the Big Bang stands out, not just for its chilling temperature, but also for the puzzles it introduces to our understanding of cosmic structure. Unlike the relatively uniform glow of the cosmic microwave background, CMB, the cold spot is strikingly cooler, deviating from the expected energy balance of the universe's earliest light. At first glance, scientists attributed this anomaly to a potential supervoid, an immense region with far fewer galaxies and matter than typical. If this void exists, it stretches light passing through it, draining photons of energy and leaving behind a colder signature in the CMB. But surveys have struggled to confirm a void large enough to account for the entire cold spot. This discrepancy invites questions. Is this void an isolated case, or does it hint at a broader cosmic phenomenon yet to be understood? Some have proposed that the cold spot is a relic of quantum fluctuations during the inflationary period of the early universe. These fluctuations, amplified as the universe expanded, may have left scars in the cosmic fabric, creating regions like the cold spot. Such a hypothesis suggests the universe's birth was far more chaotic and uneven than the current models allow. It challenges assumptions about the smoothness of inflation and opens the door to discussions about how the universe's initial energy distribution shaped its evolution. Another possible explanation is that this mark is the result of a collision with a different universe. Though theoretical, this concept originates from multiverse theories, which postulate that observable qualities of one reality can be affected by those of another on rare occasions. If the cold spot is an actual representation of this kind of collision, it would reshape our position within the cosmos and prove the existence of other worlds. The so-called axis of evil, an unforeseen alignment of certain patterns in the CMB, and its possible link to the cold spot further add to the enigma. On a grand scale, the cosmic microwave background, CMB, should look random, yet these alignments point to a possible link to enormous cosmic structures or invisible forces molding spacetime. Whether the cold spot's location along this axis is purely fortuitous or symptomatic of a bigger, more coherent phenomena remains an open subject. The sheer size of the cold spot, spanning 1.8 billion light-years, magnifies its significance. Few other phenomena in the observable universe compare in scale, making it a key test case for our cosmological models. Its gravitational influence, if linked to a supervoid, could bend light from distant galaxies, an effect detectable through gravitational lensing. Yet, observations of galaxies near the cold spot haven't fully aligned with these expectations, suggesting complexities beyond simple explanations. X-ray emissions from the regions around the cold spot also stand out. These emissions deviate from typical patterns observed in other voids, hinting at unique interactions between matter and radiation within or near this anomaly. If verified, these emissions could reveal hidden properties of the cold spot, including interactions involving dark energy or exotic matter. Compared to surrounding areas, this region exhibits unusually low entropy, suggesting it might operate under conditions unlike any other cosmic environment. This deviation might influence the development of galaxies and stars within or near the cold spot, potentially altering their life cycles and properties. If the cold spot is indeed linked to a supervoid, its structure is likely complex. Rather than being an empty shell, it might contain subvoids or intricate patterns of sparse matter. These irregularities could create patchy distortions in the CMB, making it challenging to attribute the anomaly to any single cause. Star formation in or near such a region could be heavily impacted. Supervoids generally see fewer new stars forming, as the lack of dense gas clouds limits the gravitational forces necessary for their creation. Galaxies within these regions might also rotate differently, their dynamics altered by the reduced gravitational pull of neighboring structures. Observations suggest galaxies near the cold spot may indeed exhibit unexpected rotational speeds or unusual star populations, though more research is needed to confirm these trends. The cold spot's connection to the cosmic web, the vast network of galaxies, filaments, and voids, adds further intrigue. It may represent a significant disruption in this web, altering the flow of matter across the universe. Time dilation effects could also play a role, as photons passing through this region experience slight shifts in their journey, warping our perception of space-time. Some far-fetched ideas suggest that the cold spot may contain energy or substance that has eluded detection thus far. Even though they are just speculations, these ideas suggest that exotic particles or quantum states might be impacting this phenomenon. The fact that the area's weak magnetic fields act differently than those predicted in other parts of the cosmos adds fuel to the fire of these debates. The cold spot's potential to alter our understanding of dark matter distribution is particularly compelling. If this anomaly is tied to a lack of dark matter, it could provide clues about how this elusive substance behaves on the largest scales. Observations of cosmic ray paths near the cold spot reveal deviations that might correlate with unseen gravitational influences, offering indirect evidence of such effects. Polarization studies of CMB photons passing through the cold spot show subtle shifts, possibly indicating interactions with gravitational fields or exotic particles. These changes, though minute, could reveal new insights into the properties of both the anomaly and the early universe. The expansion rate of the cold spot's associated void, if it exists, could also challenge existing models. Voids expand as the universe grows, but any irregularities in this process might hint at differences in the underlying properties of spacetime. The cold spot might even affect our understanding of the reionization era, the period when the universe transitioned from darkness to light as the first stars ignited. If linked to ancient voids, the cold spot may have disrupted this process, creating regions of delayed or altered star formation. Speculative yet fascinating, some theories propose the cold spot could preserve evidence of exotic interactions between photons and previously undetected particles, such as axions or sterile neutrinos. These interactions might explain its distinct properties while offering a window into unexplored areas of physics. Spacetime around the cold spot also seems warped, with deviations from predictions made by general relativity. These distortions might hint at new gravitational phenomena or previously unknown interactions between mass and energy. Gravitational waves linked to the cold spot could also provide crucial evidence of its origins. If such waves exist, they might trace back to events that shaped this anomaly, such as collisions between large-scale cosmic structures or quantum fluctuations during inflation. The cold spot provides a one-of-a-kind opportunity to test cosmological hypotheses due to its size and intricacy. It could be more than an oddity. It could hold the secret to the cosmos's big-scale dynamics, the history of the universe, and the nature of space-time. Further research into it should lead to the discovery of hitherto unknown facts about the universe, expanding our understanding of its vastness. Planetesimal collision fields. In the vastness of space, regions where young star systems are born are anything but peaceful. Planetesimal collision fields represent chaotic arenas of high-speed impacts where small rocky bodies collide with unimaginable force. These fields are critical in shaping the architecture of star systems, but also serve as reminders of the violence inherent in cosmic creation. In these zones, the energy released from even a single collision can vaporize rock and metal, sending shockwaves through the surrounding material. Such collisions are not rare. They occur repeatedly, often creating cascading events where debris from one impact collides with other objects, fueling an unending cycle of destruction and growth. The debris generated in these collisions doesn't simply vanish. It forms dense clouds of pulverized material, which can obscure light and hinder observations. Within these clouds, the fine dust may coalesce into new objects, giving birth to chondrules, tiny spherical inclusions that often become part of meteorites. These collisions also alter the chemical makeup of the involved bodies, forming exotic minerals and compounds that would otherwise not exist. This process not only shapes the physical appearance of the planetesimals, but also influences the broader chemical diversity of the star system. The motion within these fields is defined by microgravity, where the weak gravitational pull allows debris to drift freely. This creates an environment of dynamic chaos, where objects of varying sizes move unpredictably, making stabilization nearly impossible. Larger collisions generate shockwaves that ripple through the field, displacing smaller fragments and further destabilizing the region. The interactions are so complex that predicting the movement of even a single planetesimal becomes a near impossible task. It's this unpredictable motion that contributes to the frequent and violent nature of these collisions. While the destruction in these fields is immense, it also serves a purpose. The process of accretion, the gradual growth of larger bodies through the accumulation of smaller fragments, is central to planet formation. Despite the destructive collisions, surviving planetesimals slowly gather mass, eventually becoming protoplanets. However, this process is far from smooth. Each collision transfers heat to the impacted body, sometimes triggering internal melting or volcanic activity. This can result in the creation of metallic cores as denser materials sink inward, further shaping the planetesimal structure. These fields aren't static. Over time, gravitational interactions with nearby massive objects, such as forming planets or stars, can destabilize the orbits of planetesimals, increasing the collision rate. In some cases, material from these collisions is ejected entirely from the system, potentially seeding other regions of space with essential building blocks for planet formation. Other debris may coalesce into irregular satellites or moons, which orbit larger bodies and bear the scars of their chaotic origins. Even though these regions are dangerous, they are crucial for understanding the early stages of planetary systems. The dust generated from collisions often forms observable rings around young stars, acting as a visual map of the star system's activity. These dust rings are not just remnants of destruction, they also influence the behavior of light and radiation within the system, shaping the conditions under which planets and other bodies evolve. Collisions in these fields also release significant heat, altering the thermal properties of the surrounding environment. This heat, combined with the chemical reactions initiated during impacts, can create organic molecules, the building blocks of life. While the conditions are hostile, they may paradoxically set the stage for habitability in later stages of the star system's evolution. However, the sheer frequency of impacts in these regions makes it unlikely that any stable environment could exist at this stage. Observing these regions offers a window into the past of our own solar system. The asteroid belt between Mars and Jupiter, for example, is a relatively calm remnant of what might have been a more chaotic collision field billions of years ago. By studying similar regions around other stars, scientists can gain insights into how the planets in our solar system came to be. The craters and fractures seen on asteroids today are evidence of countless collisions, each one a testament to the violent processes that shaped them. But it's not just about the individual bodies. The collective behavior of these fields plays a critical role in clearing protoplanetary disks, paving the way for planets to form. Over time, the debris fields thin out as material either coalesces into larger bodies or is ejected from the system. This transition from chaos to order is a defining moment in the life of a star system, marking the shift from a violent nursery to a more stable environment. The remnants of these collisions often find their way to Earth as meteorites, carrying with them records of their violent origins. These space rocks contain unique mineral compositions and structural features that reveal the high-energy impacts that created them. By studying these meteorites, scientists can reconstruct the history of the planetesimal collision fields from which they came, offering clues about the conditions in early star systems. The violence of these regions isn't confined to their immediate vicinity. Streams of microscopic particles, ejected from collisions, spread throughout the star system. These cosmic dust streams influence the evolution of the system, interacting with radiation and magnetic fields. In some cases, they may even contribute to the formation of secondary structures, such as additional rings or disks around the central star. The density of planetesimals in these fields varies, creating zones of intense activity and relative calm. This variability shapes the dynamics of the region, with denser areas experiencing more frequent collisions. In these hotspots, the likelihood of chain reactions increases, with one collision triggering multiple others in quick succession. These high-density zones are where the most significant growth and destruction occurs. Collisions in these fields don't just shape the physical structure of the involved bodies. They also leave behind evidence in the form of impact craters and shocked minerals. These features provide a permanent record of the intense pressures and temperatures generated during collisions. Studying these features helps scientists understand the conditions under which these impacts occur and their long-term effects on the bodies involved. The energy released during these collisions is immense, sometimes rivaling the output of small stars. This energy drives outflows of charged particles, creating localized radiation storms. These outflows interact with the magnetic fields of nearby objects, generating complex electromagnetic phenomena. In some cases, these interactions may even influence the behavior of the central star, further shaping the star system's evolution. The chaotic nature of planetesimal collision fields poses challenges for exploration. Any spacecraft venturing into these regions would face extreme risks from high-speed debris. Even small particles, traveling at tens of kilometers per second, could cause catastrophic damage. Navigating these fields requires advanced technology and precise calculations to avoid the most dangerous zones. Despite the risks, these fields hold immense scientific value. They are laboratories for studying the processes that govern the formation and evolution of star systems. By observing these regions, scientists can test theories about how planets form and evolve, gaining a deeper understanding of the forces that shape the universe. Stripped galactic cores. The universe hides extraordinary dangers within its vast expanse. Stripped galactic cores are some of the most haunting reminders of the cosmos's violent nature. These remnants are the bare skeletons of galaxies, left behind after stars and gas have been ripped away. What remains is an environment dominated by dense star clusters, exposed supermassive black holes, and chaotic gravitational forces. At the heart of many stripped galactic cores lies a supermassive black hole, now fully exposed without the shielding of gas or stellar layers. These black holes, once shrouded in the activity of their parent galaxies, become intense sources of X-ray and gamma-ray emissions. With no intervening matter to block their radiation, they unleash a flood of high-energy particles across intergalactic distances. Any object venturing too close would face complete disintegration from the sheer energy radiating outward. Surrounding these black holes are stellar remnants locked in tight orbits. The lack of intervening gas means stars within these cores are often ancient, compact, and densely packed. Their gravitational interactions with one another are chaotic, leading to a higher chance of stellar collisions. When stars collide, they can merge or trigger intense thermonuclear reactions, resulting in unique phenomena like blue stragglers. These collisions also produce bursts of heavy elements, enriching the intergalactic medium with rare materials. The gravitational chaos extends to nearby systems, as the stripped core's intense pull distorts the motion of stars, planets, and even other galaxies. Stripped galactic cores are powerful sources of gravitational waves, generated when compact objects like neutron stars or black holes within the core interact or merge. These ripples in space-time travel across the universe, carrying signatures of their violent origins. In addition to their gravitational effects, stripped galactic cores are also major accelerators of particles. With little gas to dampen the activity of the black hole's accretion disk, these cores can act like colossal particle accelerators. Jets of plasma are ejected at near light speeds, carving through the surrounding void. These jets, much like those from Blazars, extend for thousands of light years, delivering radiation that could sterilize entire regions of space. However, stripped cores are more than simply trash dumps. They are cosmic laboratories that store information on how galaxies have evolved. They show the remnants of old mergers, when galaxies smashed into each other and ripped each other apart, leaving behind scars of star and material debris. Compact objects such as neutron stars and white dwarfs, which are remnants of the first galaxies, are contained within the core that persists. Astronomers can learn about the early phases of galaxy creation from these relics. The tidal effects of stripped cores often leave behind trails of stars and debris. These tidal streams extend across vast distances, forming faint ethereal structures visible under specific wavelengths of light. Each stream acts like a breadcrumb trail, leading scientists to understand how galaxies interact and cannibalize one another. Dense populations of white dwarfs and neutron stars within stripped galactic cores make them hotspots for rare astrophysical events. Type Ia supernovae are common in these regions, triggered when a white dwarf accretes enough material from a companion to exceed its critical mass. These supernovae release immense amounts of energy, outshining entire galaxies for a brief moment. The cores also harbor pulsars, rapidly spinning neutron stars emitting beams of radiation. These pulsars, when isolated in stripped cores, are excellent tools for studying the universe's magnetic fields and the distribution of matter. While stripped cores are devoid of gas for new star formation, their environments are anything but quiet. The remaining stars often show unusual compositions, reflecting their origins in ancient galaxies. Their light carries clues about the chemical makeup of the early universe, including the presence of rare heavy elements formed in supernovae or neutron star mergers. Stripped cores can also act as gravitational traps, pulling in intergalactic debris. This debris, composed of gas, dust, and smaller celestial objects, forms faint accretion structures around the core. Over time, these structures may reignite star formation under specific conditions, briefly turning a quiet core into a hotspot of activity. However, in most cases, the stripped core remains a stark, barren environment. The remnants of dark matter halos surrounding stripped galactic cores also intrigue scientists. These halos, which once encompassed entire galaxies, are often distorted by the violent stripping process. Observing these halos helps astronomers map the distribution of dark matter and understand its role in galactic dynamics. The stripped cores also serve as the origin points for ultra-luminous X-ray sources, ULX. These sources, often associated with black holes or neutron stars, emit radiation so intense that it challenges our understanding of energy release in the universe. Without gas to obscure these emissions, stripped cores become beacons, broadcasting their deadly energy across vast distances. Another degree of mystery is added by galactic wanderers, sometimes known as renegade stripped cores. These cores float in cosmic space once they are released from their gravitational bonds to a parent galaxy. Their impact on neighboring matter is tremendous, yet they are difficult to observe due to their seclusion. A rogue stripped core's actions can cause starbursts, perturb the orbits of other galaxies, or even amplify the light from faraway objects by virtue of its gravitational lensing. While stripped galactic cores represent destruction, they also symbolize survival. Despite losing their stars, gas, and structure, these cores persist as remnants of galactic evolution. They embody the resilience of the universe, enduring even after catastrophic events. The interplay of gravity, radiation, and particle acceleration within these cores creates one of the universe's deadliest environments. Yet, these remnants are vital to understanding cosmic history. By studying stripped galactic cores, we gain a clearer picture of the forces shaping galaxies and the extreme conditions that define the universe's most dangerous places. From gravitational waves to rogue hypervelocity stars, the phenomena linked to stripped galactic cores reveal the dynamic and violent processes driving the cosmos forward. Supermassive star-forming regions. Massive molecular clouds hang in space as cradles of star formation, dense with the gas and dust that fuel cosmic creation. Within these regions, conditions are ripe for the formation of the most massive stars in the universe. But these supermassive star-forming regions are anything but peaceful. Instead, they are arenas of extreme violence, with intense ultraviolet radiation, shock waves, and magnetic fields creating zones of destruction that leave little room for survival. Here, massive protostars dominate, emitting ultraviolet radiation that ionizes the surrounding hydrogen gas, sculpting glowing HII regions that stretch for hundreds of light years. The energy released by these young stars doesn't simply light up the area. It disrupts, sterilizes, and obliterates. The radiation pressure alone in these regions reshapes the environment, pushing gas and dust outward with immense force. While this might seem like cosmic housekeeping, it's actually chaotic, sending shockwaves through nearby clouds and creating turbulence that prevents some stars from forming. Yet, paradoxically, these same pressures can trigger star formation in other regions by compressing gas into new dense pockets. This feedback loop is the lifeblood of star-forming regions, a balance of creation and destruction. Within these zones, the density of stars is staggering. Hundreds or even thousands of young stars can cluster within a single region, separated by mere fractions of a light year. This density amplifies the ultraviolet radiation, stellar winds, and gravitational interactions, creating a volatile environment where collisions are not only possible, but inevitable. Protostellar collisions, for instance, release bursts of energy that reshape the immediate area, leaving trails of disrupted gas and debris. Stars of this mass have a brief lifespan and a rapid demise in these areas. Supernovae are the result of their rapid depletion of nuclear fuel, which occurs within a few million years. The devastation and creation are intensified when these explosions cause shockwaves to travel through space, which in turn compresses gas in the area and in rare cases sets in motion the process of star formation. Supernova remnants, which are rich in heavy elements, also plant the seeds for new planetary systems to form in the universe. Even in the face of total devastation, these areas provide the blueprint for future planets. Amid the chaos, the role of magnetic fields cannot be overstated. They shape the flow of gas and dust, sometimes trapping material in turbulent vortices or accelerating particles to extreme speeds. These fields also influence the jets of material ejected from forming stars, creating bipolar outflows that collide with the surrounding gas and dust. These outflows are not gentle. They generate shockwaves that ripple through the region, stirring up more turbulence. Supermassive star-forming regions are often enshrouded in thick clouds of dust, obscuring them from visible light. However, their activities are revealed in infrared and radio wavelengths, where astronomers detect the heat of forming stars and the complex motions of gas clouds. The energy output of these regions is staggering, with some shining brighter than entire galaxies. Starburst galaxies, for example, are home to regions of star formation so intense that they produce hundreds of times more stars than the Milky Way in a given period. The sheer scale of these regions makes them visible across vast cosmic distances, acting as beacons of violent creation. But for any planetary systems forming in these regions, survival is a near impossibility. The intense radiation from massive stars strips away the material from protoplanetary disks, halting planet formation in its tracks. Any fledgling planets that do form are bombarded by radiation and stellar winds, leaving them barren, scorched, or even completely disintegrated. These environments are hostile to even the hardiest attempts at planetary development. The presence of hypergiants, stars over 100 times the mass of the Sun, further heightens the danger. These stars dominate their regions, their gravitational influence shaping the orbits of nearby stars and gas clouds. When they finally collapse, some may skip the supernova phase entirely, forming black holes that continue to exert influence over their surroundings. In these regions, binary and multiple star systems are common. The gravitational interactions between these stars create additional instability, with stellar mergers sometimes releasing enormous bursts of energy. The merger of two massive stars can briefly outshine an entire galaxy, a testament to the energy concentrated in these regions. Gamma-ray bursts, though rare, are another potential hazard. These bursts, which may originate from the collapse of massive stars or the merger of stellar remnants, can bathe entire regions in high-energy radiation, sterilizing everything in their path. For a forming star cluster, such an event would be catastrophic, halting star formation and destroying any emerging systems. The chaotic motion of gas and dust within these regions also leads to hydrodynamic instabilities. These instabilities ripple through the clouds, creating vortices and shock fronts that churn the material and reshape the landscape. This dynamic environment means that the structure of star-forming regions is constantly changing, with dense pockets of gas collapsing under gravity, while others are blown apart by radiation and winds. Chemical complexity is another hallmark of these regions. While the intense radiation breaks apart many molecules, the dense, shielded areas allow for the formation of complex compounds, including organic molecules. These molecules, though fragile, offer a glimpse into the chemistry that might precede the formation of life in less hostile environments. Supermassive star-forming regions are extremely intense because of their transient nature. The gas and dust in these areas is usually only there for a few million years, until it's scattered by feedback from huge stars. The heavy, element-rich leftovers of these areas play a role in galactic development by providing the material for new stars and planets to form. In some cases, the feedback from star-forming regions expels gas at hundreds of kilometers per second, shaping the surrounding galaxy. These outflows can carry material far from the region, influencing star formation on galactic scales. Yet, despite their destructive tendencies, these regions play a crucial role in the cosmic cycle, turning raw material into stars, heavy elements, and the building blocks of future systems. The balance of forces in these regions is delicate. Radiation, gravity, magnetic fields, and turbulence all interact in a complex dance that determines the fate of the gas and dust. This interplay creates structures like pillars, cavities, and filaments, which reveal the underlying forces at work. The iconic pillars of creation in the Eagle Nebula are a small-scale example of the structures that can form in these environments, shaped by radiation and winds from nearby massive stars. As time progresses, the star clusters formed in these regions gradually disperse, their stars drifting apart under the influence of gravity and galactic tides. These stars carry the imprint of their origins, enriched with heavy elements and shaped by the chaotic environment in which they formed. Supermassive star-forming regions are not isolated phenomena. They often interact with their surroundings, influencing nearby regions of space. The shock waves and outflows from these regions can trigger star formation in adjacent clouds, creating a ripple effect that spreads across tens or hundreds of light years. This interconnectedness highlights the role of these regions as engines of galactic evolution. These regions are also sites of extreme contrast. While the outer edges might be cold and dark, the cores are among the hottest and brightest places in the universe. This dichotomy underscores the complexity of these regions, where creation and destruction occur side by side. Even after the stars have dispersed and the gas has been blown away, the legacy of supermassive star-forming regions persists. The heavy elements they produce enrich the interstellar medium, laying the groundwork for the next generation of stars and planets. In this way, these regions, though deadly and chaotic, are also foundational to the universe's ongoing evolution. Shock fronts in galaxy cluster collisions. The universe is filled with zones of unthinkable chaos, and shock fronts in galaxy cluster collisions are among the most extreme. When two galaxy clusters collide, the aftermath sends ripples of destruction through millions of light years. The gas in these regions is superheated to tens of millions of degrees, generating X-rays so intense they can sterilize any nearby systems. This heat isn't a simple byproduct. It transforms the intergalactic medium, creating reservoirs of plasma that can persist for billions of years. In these collision zones, gravitational forces pull apart galaxies caught in the crossfire. Stars are flung from their orbits, and the molecular gas needed for star formation is stripped away. These are not localized events but colossal interactions that fundamentally reshape entire regions of space. The shock waves themselves compress and destroy gas clouds, obliterating star-forming potential in some areas while triggering violent bursts of star formation in others. Yet, these newly formed stars often face harsh conditions. bombarded by the surrounding radiation and the residual turbulence of the collision. As the shock fronts spread outward, they amplify magnetic fields within the intergalactic medium. This process creates zones of high-energy particle acceleration, producing cosmic rays that can travel across the universe. These particles carry with them the history of their violent origins, bombarding other regions of space with the echoes of their destructive birth. Some of these cosmic rays even find their way to galaxies like ours, impacting planetary atmospheres and leaving traces of their journey. The scale of these collisions is so vast that the shock fronts act like cosmic sound waves, albeit at frequencies far below human perception. These waves ripple through the surrounding gas, creating turbulence and redistributing matter over colossal distances. This turbulence is not just chaotic. It reshapes the structure of the clusters, determining how they evolve over billions of years. The gravitational forces in these zones are immense, warping space-time and producing lensing effects that allow us to observe distant galaxies. This lensing provides a rare opportunity for astronomers to map the distribution of dark matter within these clusters. However, the same forces that give us this insight are capable of tearing apart smaller galaxies caught in the gravitational crossfire, leaving only remnants scattered across the cosmic battlefield. These regions are also hotbeds for the acceleration of charged particles, generating radio waves detectable across intergalactic distances. The interaction between magnetic fields and high-energy particles in these shock fronts turns them into natural particle accelerators, creating emissions that reveal the extreme conditions at their core. In some cases, gamma-ray bursts, brief but extraordinarily powerful, are observed, adding yet another layer of danger to these regions. The collisions don't just destroy, they also create. The compression of gas clouds within these zones sometimes triggers bursts of star formation, but this creation comes at a cost. These newly formed stars are born into an environment hostile to life, bathed in radiation, and subjected to the gravitational chaos of the surrounding cluster. The effects on nearby galaxies of these collisions are even more disturbing. Rather than being local, the shock waves go out into space, crashing with galaxies that are millions of light-years distant. This process depletes these galaxies of their molecular gas, rendering them incapable of star formation. These collision zones also enrich the intergalactic medium with heavy elements. As stars are destroyed and gas clouds are compressed, the metals forged in stars are dispersed across the region. This enrichment plays a role in the evolution of future stars and galaxies, but comes at the cost of unimaginable destruction. As the energy of the collision dissipates, it leaves behind an altered environment. The entropy of the region increases, changing the thermodynamic state of the clusters. These areas remain hot for billions of years, acting as cosmic scars that testify to the violent processes that shaped them. The gravitational effects of these collisions extend beyond the clusters themselves, influencing the structure of the cosmic web. The filaments of gas and matter that connect galaxy clusters are shaped and reshaped by these interactions, creating pathways through which material flows across the universe. Collisions can sometimes even wake up latent black holes in the clusters. As more gas and matter enters these areas, black holes are prompted to release strong relativistic jets, which further disturb the local ecosystem. Planets' atmospheres can be vaporized, and anything in their way can be wiped out by these jets. Massive buildings aren't the only targets of these accidents' devastation. Intense radiation and heat evaporate dust grains in the collision zones, changing the intergalactic medium's composition on a smaller scale. Since dust is a fundamental component of star and planet formation, its annihilation has consequences for the process of star and planet formation in the future. These shock fronts are not just destructive, but also provide invaluable data for scientists. By studying the temperature and velocity variations within these zones, astronomers can map the movement of stars and gas, gaining insights into the dynamics of galaxy clusters. The patterns of X-ray emissions reveal the thermal structure of the clusters, offering clues about their history and the processes that drive their evolution. But the danger isn't confined to the immediate aftermath of the collision. The particles and radiation generated in these zones travel far beyond their origin, impacting regions of space that may seem distant and unrelated. Cosmic rays seeded by these shock fronts contribute to the high-energy particle population across the universe, affecting planetary systems and even the atmospheres of distant worlds. The energy released in these collisions is so immense that it creates observable changes in the luminosity of the affected clusters. The brightness of these regions spikes during the collision, providing a temporary but striking reminder of the immense forces at play. These luminosity changes, combined with gravitational lensing effects, allow astronomers to study the interactions in detail, turning these deadly zones into windows into the universe's most extreme events. The cosmic voids encircling the clusters are likewise affected by the expansion of these shock fronts. When matter is pushed outward, it generates pressure waves, which enlarge these spaces and change the cosmic distribution of matter. A crucial component of the universe's large-scale structure is this interplay between clusters and voids. Through all this destruction, the shock fronts in galaxy cluster collisions serve as a stark reminder of the universe's raw power. They are zones of creation and annihilation, shaping the evolution of galaxies, stars, and the very fabric of the cosmos itself. These regions stand as some of the most hostile places in the universe, yet they also provide crucial insights into the processes that govern it. The energy and chaos unleashed in these collisions ripple across the cosmos, influencing everything from the smallest particles to the largest structures. Cosmic string wakes. The remnants of stripped galactic cores, dense with exposed black holes and star clusters, reveal a grim reality of gravitational chaos. When these stripped cores drift into cosmic string wakes, their already hazardous environments become zones of unparalleled destruction. The gravitational fields of these hypothetical strings amplify the chaos, pulling matter into violent collisions and igniting intense bursts of energy. These wakes, believed to be relics from the early universe, stretch like scars across space-time, distorting and bending everything in their vicinity. Cosmic string wakes are not visible like a glowing star or an energetic Pulsar wind nebula. Instead, their effects are felt across light years, evident in distorted light patterns and disrupted orbits of celestial bodies. As light from distant stars passes near a cosmic string wake, it bends and splits, creating gravitational lensing effects. These distortions offer astronomers a glimpse into these enigmatic forces, showcasing the immense power of gravitational fields, strong enough to bend the path of light itself. Compressing matter into dense filaments is one of the most remarkable results of cosmic string wakes. The likelihood of star formation increases dramatically in areas where dust and gas are compressed together. Having said that, it is everything but peaceful. A hostile environment is created where stars are formed under enormous stress as shockwaves produced by the wake heat the gas to high temperatures, releasing X-rays. New stars are born into these areas, which are simultaneously places of creation and destruction because of the chaotic origins of the star's radiation and gravitational perturbations. The wakes also influence the alignment and movement of entire galaxy clusters. Evidence suggests that some large-scale structures in the universe may owe their formation to the pull of cosmic strings. As clusters of galaxies drift through these wakes, their paths are subtly altered, creating alignments that hint at the presence of these invisible forces. This effect isn't just limited to galaxies. Rogue planets, stripped of their host stars, can also be dragged into the chaos. These lonely wanderers, already adrift in interstellar space, face further instability as they encounter gravitational distortions that send them hurtling through space at even greater speeds. The energetic processes within a cosmic string wake often resemble those found in shock fronts of galaxy cluster collisions. In both cases, high-energy particles are accelerated to near-light speeds, bombarding their surroundings with deadly radiation. These particles, often stripped electrons and protons, move through the intergalactic medium, ionizing gas and creating fields of radiation inhospitable to any form of life. The sheer energy involved in these processes is staggering, with temperatures and particle velocities reaching levels that make even the most extreme environments within a star seem tame. Cosmic string wakes also have the potential to disrupt the delicate balance of protoplanetary systems. Young systems, where planets are still forming from disks of gas and dust, are particularly vulnerable. A passing wake can strip away these materials, halting the formation process and leaving behind a barren star surrounded by remnants of what might have been a vibrant planetary system. This destruction extends to the planetary level, where gravitational forces can tear apart even fully formed worlds. Theoretical studies suggest that the ends of cosmic strings, if they collapse, could release bursts of energy in the form of Hawking radiation. These events, while hypothetical, provide a stark reminder of the extreme nature of these objects. The radiation from such a collapse could rival the energy output of a supernova, creating a momentary but deadly flash that would sterilize anything within its reach. These bursts, if observed, could provide direct evidence of cosmic strings and their devastating potential. On a grander scale, cosmic string wakes cause galaxy clusters to shift, which in turn causes ripple effects that stretch for millions of light years. The enormous events that caused these interactions to occur impart knowledge about them via gravitational waves, which are essentially ripples in space-time. Cosmological string wake waves, in contrast to those produced by neutron star collisions or double black holes, would be fainter but more distant, providing a new angle on the cosmos's dynamics. The deadly nature of cosmic string wakes is further emphasized by their ability to create voids in the cosmic web. As matter is pulled into dense filaments along the wake, vast regions of space are left devoid of material. These voids, stretching across millions of light years, are regions where the density of matter drops to near zero. While seemingly empty, these voids still bear the gravitational imprint of the wakes that formed them, subtly influencing the movement of galaxies and stars along their edges. Despite their invisibility, cosmic string wakes leave behind a trail of evidence that astronomers can detect. From gravitational lensing to the alignment of galaxies, these features offer clues about the presence and behavior of these enigmatic forces. Advanced telescopes and simulations continue to refine our understanding, revealing the intricate web of interactions that shape the universe on its largest scales. In the end, cosmic string wakes serve as a reminder of the interconnectedness of all cosmic phenomena. They bridge the realms of theoretical physics and observational astronomy, offering a glimpse into the forces that shaped the early universe and continue to influence its evolution. Hypervelocity star paths. In the chaotic landscape of the universe, hypervelocity star paths weave tales of destruction, disruption, and incredible power. These trails, carved by stars flung at unimaginable speeds, unravel entire systems, leaving chaos in their wake. The origins of these speeding stars often lie deep within galactic cores, where interactions with supermassive black holes act as colossal slingshots. In binary systems, this process is even more striking. One star may be hurled out at hypervelocity, while its companion is captured, forever bound to the gravitational grasp of the black hole. As these stars escape their galaxies, they move faster than the galaxy's escape velocity, sometimes exceeding 1,000 kilometers per second. Their speeds alone transform them into cosmic disruptors, destabilizing planetary systems they pass through. Planets and moons, caught in the grip of their intense gravitational pull, may be ejected from their orbits, becoming rogue wanderers of interstellar space. The debris they leave behind forms a testament to the havoc they cause, a trail of disrupted systems and scattered remnants. Hypervelocity stars do more than disrupt, they create. The shockwaves generated as they move through dense interstellar regions compress gas clouds, sparking new waves of star formation. Ironically, these agents of destruction also give birth to new celestial bodies. Their wakes, filled with ionized gas, glow with radiation, marking their paths like luminous signatures across the cosmos. Many hypervelocity stars leave their home galaxies entirely, venturing into the void of intergalactic space. In their isolation, they carry with them the chemical fingerprints of their origins, offering a glimpse into the history of the galaxies they once belonged to. These stars, untethered and solitary, become rare beacons that illuminate the vast distances between galaxies, their brightness cutting through the emptiness of intergalactic space. In some cases, clusters of hypervelocity stars are ejected together, their shared trajectories hinting at massive gravitational events. These clusters can interact with other galactic structures, scattering stars and triggering gravitational disturbances. Such encounters not only reshape individual systems, but also contribute to the evolution of entire galaxies. The interactions of hypervelocity stars are not limited to planets and stars. When they pass through molecular clouds, their immense energy disturbs star-forming regions, halting or accelerating the birth of stars. Their motion can also compress cold gas clouds, creating conditions for new stellar nurseries. This dual role, both destructive and generative, cements their place as pivotal players in the cosmic ballet. Hypervelocity stars are not confined to predictable patterns. Some may carry remnants of binary systems, with both stars maintaining their orbits as they travel at extreme speeds. These rare systems challenge our understanding of stellar mechanics, offering a glimpse into the resilience of gravitational bonds even under extreme conditions. Others collide with stars in dense regions, resulting in cataclysmic explosions that release enormous amounts of energy and material into the surrounding space. Their influence extends beyond their immediate surroundings. In galactic halos, hypervelocity stars interact with dark matter, leaving subtle gravitational imprints that help map this elusive component of the universe. The energy from their ejections also redistributes momentum within galactic cores, influencing the dynamics of supermassive black holes and the stars that orbit them. Not only do hypervelocity stars play important roles in our universe, but they also provide light on deeper cosmic puzzles. Details regarding the mass distribution and gravitational forces are revealed by their paths, which offer insights into the structure of galaxies. Along with providing proof of missing baryonic matter, their cosmic travels reveal areas with lower concentrations of conventional matter. Some hypervelocity stars originate not from major galaxies, but from smaller, consumed dwarf galaxies. These stars, flung out during galactic mergers, carry the chemical signatures of their original homes, acting as time capsules of galactic evolution. As they move through intergalactic space, they spread elements from their former galaxies, contributing to the chemical enrichment of the universe. Their immense energy amplifies stellar wind effects, creating extended trails of charged particles. These winds interact with the interstellar medium, creating zones of increased radiation and magnetism. Such interactions can enhance the visibility of hypervelocity stars, making them detectable across great distances. Hypervelocity stars might also play a role in cosmic ray acceleration. As they travel through dense gas or magnetic fields, their energy may contribute to the production of high-energy particles that eventually reach Earth. This link between their motion and cosmic ray production underscores their far-reaching influence. In some instances, entire binary systems are ejected together, adding a layer of complexity to their dynamics. These binaries might maintain their orbits even as they travel at extreme speeds, their gravitational bonds surviving the forces that expelled them. Such systems provide unique opportunities to study stellar evolution under conditions far removed from the gravitational constraints of a galaxy. The paths of hypervelocity stars intersect with a variety of celestial objects, including rogue planets and neutron stars. These encounters can alter trajectories, create gravitational disturbances, and even strip material from smaller objects. The cascading effects of such interactions ripple through space, affecting systems far removed from the initial encounter. The alignment of these long-gone characteristics is disturbed when these stars contact stellar streams. hypervelocity stars, exhibit their ability to impact galactic evolution on a grand scale by dispersing stars inside streams, which reshapes these structures. Hypervelocity stars occasionally collide with dense gas clouds or accretion disks around black holes, disrupting their flow and sparking emissions that can be detected from Earth. These interactions, while brief, release vast amounts of energy, creating bursts of light and radiation that serve as markers of these stars' incredible journeys. Despite their rarity, hypervelocity stars are crucial to understanding the energy dynamics of galaxies. Their ejections redistribute energy within galactic cores, influencing the motion of other stars and the growth of central black holes. These stars are not mere outliers, but integral to the processes that shape galaxies. Some hypervelocity stars may even contribute to the formation of smaller galactic halos, their interactions with intergalactic material creating conditions for the coalescence of new structures. These halos, though faint, represent another way in which hypervelocity stars leave lasting imprints on the universe. Their ejection events also have the potential to generate gravitational waves, particularly when they involve interactions with massive objects like black holes. These waves add to the growing body of evidence we have for violent cosmic events, further enriching our understanding of the universe's dynamic processes. Hypervelocity stars challenge the stability of planetary systems, their close encounters creating gravitational disruptions that can eject planets or alter orbits. These disruptions extend to moons and asteroids, adding to the cascading effects of a passing hypervelocity star. Even the magnetic fields of hypervelocity stars can have profound effects. As they move through regions with strong magnetic activity, they create localized disturbances that ripple outward, affecting nearby systems. These magnetic interactions further underscore the multifaceted nature of their influence. Each hypervelocity star carries a story of cosmic extremes, their paths shaped by the immense forces that dominate the universe. As they traverse galaxies and intergalactic space, they connect disparate regions of the cosmos, linking events and systems in ways that underscore the interconnectedness of everything. Orphaned neutron stars. The vastness of intergalactic space holds mysteries that often defy human understanding. As we move beyond the paths of hypervelocity stars, ripping through their surroundings at unimaginable speeds, another perilous phenomenon emerges. Orphaned neutron stars. These compact remnants of massive stars are the outcasts of their kind, ejected from galaxies during violent cosmic events. They drift alone through the void, carrying with them the scars of their turbulent origins and posing unique dangers to anything unfortunate enough to cross their paths. When a massive star dies in a supernova, the resulting core collapses into a neutron star, an object so dense that a single sugar cube-sized piece would weigh as much as a mountain. Most neutron stars remain tethered to their home galaxy, but in some cases, the explosion propels them outward at incredible speeds. These orphaned neutron stars can travel hundreds of kilometers per second, fast enough to escape the gravitational pull of their galaxy. Once set adrift in intergalactic space, they become rogue agents of destruction. The journey of an orphaned neutron star is marked by its interactions with the matter it encounters. These stars possess magnetic fields trillions of times stronger than Earth's, creating powerful electromagnetic storms around them. As they move through interstellar dust clouds, their magnetic fields can accelerate charged particles to near-light speeds, producing intense synchrotron radiation. This radiation bathes their surroundings in high-energy X-rays and gamma rays, sterilizing any potential habitable environments nearby. Despite their solitary nature, orphaned neutron stars leave behind detectable traces. Their paths through interstellar dust and gas create ionized trails, glowing remnants that stretch across light years. These trails not only mark their movements, but also provide astronomers with clues about their velocities and trajectories. By studying these remnants, scientists can trace the violent events that ejected these stars, shedding light on the dynamics of the galaxies they once belonged to. Sometimes, star-forming molecular clouds, dense areas of gas, are encountered by orphaned neutron stars. Localized bursts of star formation are set off when a neutron star moves through one of these clouds, its tremendous gravitational force compressing the gas. Nevertheless, neutron star radiation frequently prevents this process from happening by ionizing the gas, which stops it from merging into new stars. Orphaned neutron stars play a dual role in the cosmos, creating and destroying. Occasionally, these stars interact with larger structures, such as galactic filaments or galaxy clusters. As they traverse these environments, their gravity disturbs the distribution of matter, creating ripples that can propagate across vast distances. These disturbances may influence the evolution of nearby galaxies, subtly altering their shapes and triggering the formation of new stars in unexpected places. Extreme cases do occur with some orphaned neutron stars. These stars are called magnetars because their magnetic fields are so strong that they may distort atomic structures. In the blink of an eye, a magnetar flare, the result of an abrupt change in its magnetic field, emits more energy than the Sun does in 100,000 years. Satellites, communication networks, and even Earth's magnetic field may be affected if this kind of flare were to happen within our galaxy. These flares are so faint that only the most sensitive telescopes can detect them in the vastness of interstellar space. Not all orphaned neutron stars are isolated. Occasionally they capture passing objects, forming temporary binary systems. These systems are short-lived, as the neutron star's gravitational pull quickly tears its companion apart, creating bursts of X-rays and gamma rays. These emissions are detectable from Earth, providing astronomers with a glimpse into the violent interactions taking place far beyond our galaxy. Orphaned neutron stars may combine with other dense objects like black holes or other neutron stars, which is one of the most interesting things about them. These magnificent yet uncommon mergers cause space-time to vibrate with gravitational waves. Scientists may now observe phenomena that were previously invisible because of the discovery of these waves, which has provided a fresh perspective on the cosmos. Short gamma-ray bursts, which may temporarily eclipse whole galaxies, are another consequence of mergers involving orphaned neutron stars. The motion of orphaned neutron stars through the intergalactic medium also provides valuable insights into the nature of this mysterious space. As these stars interact with the sparse matter between galaxies, they create bow shocks, regions where their high-speed movement compresses and heats the surrounding gas. These bow shocks emit faint radiation, revealing the density and composition of the intergalactic medium. By studying these emissions, astronomers can learn more about the structure and evolution of the universe. Orphaned neutron stars also serve as natural laboratories for studying extreme physics. Their immense densities and magnetic fields create conditions that cannot be replicated on Earth. For example, the cores of neutron stars may contain exotic forms of matter, such as quark-gluon plasma, a state where protons and neutrons break down into their constituent quarks. By observing the behavior of orphaned neutron stars, scientists can test theories about the fundamental nature of matter. In rare cases, an orphaned neutron star may encounter a supermassive black hole. If the star is captured by the black hole's gravity, it is gradually torn apart. These events produce luminous flares that can outshine the combined light of all the stars in a galaxy. While such encounters are incredibly rare, they highlight the interconnectedness of even the most isolated objects in the universe. As orphaned neutron stars traverse the cosmic landscape, their interactions with other objects and structures leave lasting imprints. They redistribute matter, generate radiation, and trigger gravitational waves, shaping the universe in subtle but significant ways. Their solitary journeys are a testament to the violent processes that govern the cosmos, reminding us of the delicate balance between creation and destruction. From their origins in supernova explosions to their roles as cosmic disruptors, orphaned neutron stars are among the most fascinating and deadly inhabitants of the universe. They are silent wanderers, carrying with them the echoes of their tumultuous pasts and the potential to alter the future of the cosmos. Supermassive binary black holes. Transitioning from the realm of orphaned neutron stars, we step into the chaotic gravitational playground of supermassive binary black holes. These colossal systems represent some of the most extreme environments in the universe, where the gravitational pull of two black holes, each with millions or billions of solar masses, dominates. Their intricate dance creates powerful ripples in space-time and reshapes the cosmic landscape around them. When these black holes orbit each other, they form a system that acts as a stellar slingshot. Stars and other celestial objects passing too close are violently ejected, often at hypervelocity speeds. These expelled stars leave their galaxies behind, traveling through intergalactic space, their trajectories forever altered. In some cases, entire solar systems are flung into the void, becoming cosmic wanderers in a universe indifferent to their fate. These binaries don't just eject stars, they also disrupt their host galaxies. The gravitational interplay between the two black holes creates turbulent zones where gas and dust, essential ingredients for star formation, are stripped away. These barren zones, devoid of material, stall the birth of new stars, effectively halting galactic evolution. The energy released by these systems during their interactions can heat surrounding gas to such extreme temperatures that it remains unable to cool and condense back into stars for billions of years. While the slow waltz of these giants may seem tranquil from afar, their movements generate some of the most detectable phenomena in the universe: gravitational waves. These ripples in space-time stretch and squeeze everything in their path as they travel outward. Detecting these waves has become a window into understanding not just the black holes themselves, but also the history of cosmic mergers that have shaped galaxies. Each wave tells a story of collisions and near misses, offering a record of the universe's violent past. In regions near the binary, the chaos intensifies. The accretion disks surrounding each black hole collide and interact, producing extreme bursts of electromagnetic radiation. These outbursts are visible across great cosmic distances, manifesting as dual-active galactic nuclei. Observing such systems provides astronomers with rare insights into the behaviors of black holes under these conditions. These emissions often peak in X-rays, making the binaries visible even when surrounded by thick clouds of interstellar dust. As the two black holes spiral closer over time, their interactions grow more intense. The energy they release during this phase can rival the output of entire galaxies. The merging process itself culminates in a burst of gravitational waves so powerful that detectors like LIGO and Virgo can sense them across billions of light years. The final merger creates a single supermassive black hole, often with a powerful recoil that can eject it from its host galaxy entirely. This ejected black hole, now traveling through intergalactic space, carries with it an entourage of stars and gas caught in its gravitational grip. These runaway black holes become cosmic nomads, reshaping environments wherever they go. Their interactions with surrounding matter create unique light echoes, delayed and distorted reflections of their previous activity, which astronomers can study to trace their paths through the cosmos. The dynamic nature of supermassive binary black holes makes them ideal testbeds for theories of spacetime and gravity. Their gravitational lensing effects amplify and distort our perception of faraway things by influencing surrounding light and matter. These lenses are like cosmic telescopes. They allow us to see galaxies that were previously inaccessible. Despite their destructive tendencies, these binaries play a crucial role in the evolution of galaxies. They act as cosmic cleaners, redistributing matter and energy throughout their environments. By ejecting material, they prevent excessive star formation in galactic cores, maintaining a balance in their host galaxies. This regulation may seem counterintuitive, but it ensures the long-term stability of galactic ecosystems. The presence of a supermassive binary black hole signals a history of galactic mergers. These binaries often form when two galaxies collide, their central black holes drawn together over millions of years. The process is not instantaneous. Instead, it unfolds over timescales that span the lives of entire star systems. The remnants of these mergers, disrupted star clusters, warped spiral arms, and vast voids of stripped material, offer clues about the histories of galaxies and the forces that shape them. The environments near these binaries are so extreme that matter behaves in ways not seen elsewhere in the universe. Magnetic fields twisted by their interactions create enormous jets of charged particles that stream out at nearly the speed of light. These jets, often visible in radio wavelengths, can extend for millions of light-years, influencing regions far beyond their origin. The jet's impacts can compress interstellar gas, triggering star formation in some areas while suppressing it in others. At smaller scales, the accretion disks around each black hole can develop instabilities due to the gravitational tug-of-war between the two. These instabilities cause rapid fluctuations in brightness, creating a dynamic light show that astronomers can observe. These flickering emissions not only reveal the mechanics of the disks, but also provide indirect evidence of the black hole's movements and interactions. As the binaries spiral inward, their orbits decay due to the energy lost as gravitational waves. The closer they get, the more intense their interactions become, leading to even higher energy emissions. These final stages are among the most violent in the universe, culminating in the formation of a single, even more massive black hole. The surrounding environment, now stripped of much of its matter, enters a quiet phase, the chaos giving way to eerie calm. The story of supermassive binary black holes is not just one of destruction, it's also a story of transformation. These systems, though deadly to their immediate surroundings, are integral to the cosmic cycle of matter and energy. They are agents of change, reshaping galaxies, influencing star formation, and driving the evolution of the universe at large. From the cataclysmic to the intricate, supermassive binary black holes connect the smallest details of space-time to the grandest scales of cosmic evolution. They are not isolated phenomena, but part of a web of forces that link galaxies, stars, and the mysterious fabric of the universe itself. The energy they release, the chaos they generate, and the transformations they induce ripple across space-time. Helium flash zones on white dwarfs. Helium flash zones on white dwarfs are violent reminders of the universe's power to create and destroy in nearly the same breath. These areas are where the steady buildup of helium on the surface of a white dwarf ignites into sudden explosive fusion. The event isn't gradual, it happens all at once, releasing a burst of energy so intense that it can temporarily make the white dwarf one of the brightest objects in its local area. It's not merely an energy release. This flash is a thermonuclear detonation on a scale that dwarfs anything we could ever replicate on Earth. The energy from these flashes is short-lived but devastating. During the flash, temperatures on the white dwarf can surge to millions of degrees Kelvin. This immense heat not only consumes the helium on the surface, but also propels shockwaves that ripple across the star's surface. These shockwaves often eject layers of the star into space, creating violent stellar winds filled with high-energy particles and debris. This ejected material contributes to the interstellar medium, enriching the surrounding space with heavier elements like carbon and oxygen. These elements later become the building blocks of new stars and planets, continuing the cosmic cycle. Yet helium flashes are unpredictable. They depend on the delicate balance of mass, temperature, and pressure on the white dwarf. In binary systems, where a companion star is transferring material onto the white dwarf, the process can accelerate rapidly. The more helium that accumulates, the more catastrophic the flash becomes. The accreted material doesn't just sit there quietly. Under the immense gravity of the white dwarf, it becomes compacted to densities and pressures that are unimaginable by human standards. When fusion ignites, it happens so quickly that the resulting explosion doesn't have time to disperse evenly. Instead, localized bursts can shoot jets of material at incredible speeds. These jets have far-reaching consequences. In close binary systems, the flash can destabilize the orbit of the companion star. The sudden release of energy changes the gravitational pull between the two objects, sometimes causing the companion to spiral inward or outward. In extreme cases, the companion star might even be ejected from the system entirely, becoming a rogue star wandering through interstellar space. The radiation released during a helium flash isn't confined to the immediate vicinity of the white dwarf. High-energy photons, including gamma rays and X-rays, travel outward at the speed of light. These emissions can ionize gas clouds in the surrounding interstellar medium, creating glowing nebulae visible across vast distances. But this ionization also carries danger. Any nearby planets, assuming they're within the habitable zone of the binary system, would be exposed to radiation levels high enough to strip away their atmospheres and sterilize their surfaces. Life, if it existed, would not survive such an event. Helium flashes are often the precursors to even more dramatic phenomena. In some cases, the white dwarf gains enough mass from its companion to reach a critical threshold known as the Chandrasekhar limit. At this point, the star's core collapses, triggering a Type Ia supernova. These supernovae are among the most powerful explosions in the universe, capable of outshining entire galaxies for weeks. While helium flashes themselves are not as destructive as supernovae, they serve as warning signs of what might follow. The aftermath of a helium flash leaves its mark on the white dwarf. The surface, once a steady layer of helium, becomes disrupted and uneven. In some cases, the flash amplifies the star's magnetic field, creating regions of intense electromagnetic activity. These enhanced magnetic fields can accelerate particles to nearly the speed of light, creating localized zones of lethal radiation around the white dwarf. Astronomers study helium flashes not just for their destructive power, but also for what they reveal about stellar evolution. The light emitted during a flash provides clues about the star's composition and structure. By analyzing the spectra of these events, scientists can identify the elements present in the ejected material. This data helps refine our understanding of how white dwarfs evolve over time and how they contribute to the chemical enrichment of galaxies. It is not simple to observe a helium flash. Minutes to hours are usually the duration of these occurrences. Fast responses from telescopes are necessary to catch helium flashes because their light curves exhibit sharp peaks and valleys. Being able to see through interstellar dust and gas is easier with X-ray and gamma-ray detectors installed in space-based observatories than with visible light. Helium flashes can happen in white dwarfs with planetary nebulae around them. A spectacular light display is produced by the interaction of the explosion with the nebula, as shockwaves illuminate the gas around. These lighted nebula are a great chance to learn about the white dwarf and its surroundings in action. These interactions frequently produce patterns and structures that show explosive asymmetry, which provide clues about the complicated mechanisms that cause helium flashes. As a natural laboratory for researching extreme physics, helium flashes can also be useful. The circumstances on a white dwarf surface during a flash are very different from what we experience here on Earth. We can learn more about how matter behaves under severe circumstances when we combine high pressures, temperatures, and the rate of fusion processes. This information is relevant to areas other than astrophysics, such as nuclear physics and the study of materials. The ejected material from a helium flash doesn't always disperse evenly. In some cases, it forms circumstellar disks around the white dwarf. These disks can persist for thousands of years, influencing the star's future interactions with its environment. If the white dwarf remains in a binary system, the disk can act as a reservoir of material, feeding the star over time and potentially triggering future flashes. We are reminded of the universe's precarious equilibrium between creation and annihilation by helium flashes. Even while they provide heavy materials to the universe, they also show how powerful even the tiniest stars can be. Even though they don't survive long, these flashes shape the evolution of galaxies, planets, and stars in their immediate vicinity. We learn more about the universe's driving forces and the complex web of relationships between its many parts as we investigate these events. Galactic coronae. The relentless radiation storms around pulsars echo the harsh extremes that can arise across the universe, but these violent phenomena pale in scale compared to the galactic coronae surrounding entire galaxies. These massive halos of superheated gas are invisible in visible light, but shine brightly in the X-ray spectrum, revealing their presence through incredible temperatures reaching millions of Kelvin. They dwarf the size of the galaxies they envelop, forming massive spherical regions where the physics of heat, radiation, and gravity combine to create a hostile environment no life could endure. Galactic coronae are far more than just a visual spectacle. They are a battlefield of energy and matter, where ionized gas dominates and high-energy particles race through magnetic fields. These halos are composed of heavy elements like oxygen, silicon, and iron, remnants of supernovae and galactic collisions that once forged stars. But in these coronae, the legacy of creation is replaced by destruction. The intense heat prevents gas from cooling, effectively halting star formation and making the regions barren of new, life-bearing systems. These halos also act as the gatekeepers of their galaxies, marking the boundary where the galactic environment meets the intergalactic medium. In this liminal space, the galactic corona siphons material from passing gas clouds or satellite galaxies, often stripping smaller galaxies of their gaseous envelopes entirely. Known as ram pressure stripping, this process leaves these satellites as bare stellar remnants, further fueling the mass and heat of the central corona. Even stars that stray too close feel the effects of these immense halos, as their atmospheres are eroded by streams of high-energy particles and plasma. The source of this searing heat and deadly radiation can often be traced to the supermassive black hole at the heart of the galaxy. Through outbursts of energy during feeding episodes, black holes eject material at immense speeds into the galactic halo, adding to the corona's chaotic composition. These outbursts can create shock waves, traveling through the corona and further heating the gas, amplifying the X-ray emissions that make these regions visible across the cosmos. The temperatures of galactic coronae ensure that they remain in a state of suspended energy for billions of years. The gas here is so hot that it emits X-rays continuously, but it takes an extraordinary amount of time for the energy to dissipate and the gas to cool. This longevity makes coronae not just an ongoing hazard, but also a record of galactic history. They hold clues about the galaxy's formation, the rate of past star formation, and even the galaxies it may have merged with over time. Galactic collisions amplify the lethality of coronae, especially in galaxy clusters where their boundaries overlap. When two galaxies interact, their coronae collide first, creating turbulent shock fronts where gas heats to even higher temperatures. These interactions not only light up the X-ray sky, but also create new flows of energy and matter that can drastically reshape the galaxies involved. In some cases, the collision of coronae can create massive jets of hot gas stretching across millions of light years, cutting through the intergalactic medium like glowing scars. These halos aren't static. Their dynamics are influenced by the magnetic fields within galaxies. Charged particles in the coronae spiral along magnetic field lines, creating a complex interplay between heat, motion, and electromagnetic forces. This can generate cosmic rays, high-energy particles that can travel across vast distances, spreading radiation well beyond the confines of the corona itself. These rays interact with nearby gas clouds, sometimes triggering unexpected bursts of heat, or even the collapse of cooler regions into new stars. But this cycle of destruction and transformation is one-sided in galactic coronae. While some regions of space promote new growth or serve as cradles for star formation, the heat and radiation in these halos create an environment where new systems cannot emerge. Instead, they act as barriers, preventing the cooling of gas clouds that would otherwise condense into stars. Even the process of gravitational collapse, which forms stars in dense regions of space, is arrested in the coronae by their intense energy. The edges of galactic coronae serve as silent witnesses to the invisible presence of dark matter. The gravity needed to hold these massive halos in place far exceeds the visible matter they contain, pointing to an unseen force maintaining their structure. By observing the movements of gas and stars at the outermost edges of galaxies, scientists can map the dark matter halos that surround them, offering some of the most compelling evidence of this mysterious cosmic substance. Not only do these coronae store dark matter, but they also hold the universe's so-called missing baryons. Stars, planets, and the intergalactic medium aren't supposed to contain most of the regular stuff that theorizes to exist in the universe. Instead, it's believed to be concealed in hot, diffuse plasma like galactic coronae. By analyzing these halos, astronomers can fill in the gaps in our understanding of the universe and the substance that has so far eluded us. Through the exchange of gas and energy, coronae link their host galaxies to the filaments of matter that stretch across the universe. Gas flows from the intergalactic medium into the corona, sometimes cooling and falling into the galaxy, while other times the heat and turbulence of the corona prevent any material from settling. This cosmic balancing act shapes the future of galaxies, determining whether they will continue forming stars or drift into quiescence. Galactic coronae aren't just passive structures. They can actively destroy or reshape the galaxies they envelop. For galaxies near the edges of large clusters, the coronae act as a shield, preventing the intrusion of hot cluster gas that would strip them bare. For smaller galaxies that venture too close to a larger neighbor, however, the corona can act as a weapon, removing gas and leaving the smaller galaxy devoid of star-forming material. This interplay of protection and destruction shows how galactic coronae govern the life and death of galaxies on cosmic scales. The particles within coronae travel at incredible speeds, often near the sound speed of hot gas, creating turbulence that transfers energy across the entire halo. This turbulence can amplify magnetic fields or create regions of denser gas, forming temporary islands of cooler matter that may later rejoin the seething chaos. These interactions are a microcosm of the larger forces at play, as the corona acts as a mediator between the galaxy and the universe at large. Even at their most quiescent, galactic coronae remain deadly. Any planetary system passing through one would be bombarded with high-energy X-rays and particles, stripping away atmospheres and irradiating any surfaces. These regions are a stark reminder of how lethal the cosmos can be, even in places far removed from the violent processes of star formation or black hole activity. When we take a cosmic view of galactic coronae, we see that they are both a wall and a bridge. They separate galaxies from one another and the cosmos beyond, but they also connect them through gas and energy fluxes. The stellar evolution and the activities of supermassive black holes have created these regions of tremendous gravitational pull, radiation, and heat. Every halo has its own unique tale to tell about the galaxy it encircles, and affects the destiny of surrounding galaxies in the process. The halo's stillness reveals something about the unseen powers at work in the cosmos. Extreme planetary magnetospheres. The magnetic storms of extreme planetary magnetospheres reveal a hidden danger within the cosmos. Unlike the protective magnetosphere surrounding Earth, these colossal fields act as engines of destruction, creating high-energy radiation zones that extend far beyond their planetary origins. Charged particles trapped in these fields move at near-light speeds, forming radiation belts that dwarf Earth's Van Allen belts. These zones are so intense that even robotic explorers would struggle to survive, as their electronics would be fried by unrelenting radiation. The auroras generated by these planets, while visually stunning, signal a deeper hazard. These immense light shows, driven by accelerated particles crashing into the planet's atmosphere, are indicators of the immense magnetic turmoil present. Unlike Earth's localized auroras near its poles, these occur on a global scale, covering vast portions of the planet with an energetic glow. The auroras reveal the constant bombardment of high-energy particles trapped by the magnetosphere, creating an environment inhospitable to life. Moons orbiting within these magnetospheres face their own challenges. For example, they can experience charged dust disruption, where tiny particles in their vicinity are energized and flung about unpredictably. Over time, this bombardment can strip these moons of material, reshaping their surfaces and even creating plasma toruses, massive rings of charged gas particles. These toruses can emit their own radiation and form mini-magnetic fields that further amplify the chaos around the planet. The magnetopause, where the planet's magnetic field meets the solar wind, acts as a violent collision zone. This boundary can create shockwaves as solar particles are deflected, leading to massive bursts of energy that radiate out into space. For planets orbiting active stars, these interactions can amplify stellar winds into radiation storms, effectively turning the magnetosphere into a weaponized shield that projects deadly waves across the system. Satellites orbiting such planets face rapid destruction. High-energy particle interactions create drag within the magnetosphere, causing orbital decay. A satellite might be operational for mere months before it succumbs to this invisible force. Even the strongest materials would struggle against the relentless radiation bombardment, making long-term exploration or observation almost impossible. For nearby objects, the danger doesn't stop at the magnetic boundary. Neighboring moons can experience electrical discharges caused by moving through the magnetosphere. These interactions induce electrical currents within metallic cores, generating heat and potentially triggering volcanic activity. The results are unstable, hazardous moons with extreme surface temperatures and electromagnetic anomalies. Planets with extreme magnetospheres are also natural amplifiers of solar activity. Solar winds and coronal mass ejections, when directed at these planets, can cause magnetic reconnection events. This phenomenon occurs when magnetic field lines snap and rejoin, releasing enormous amounts of energy. In these cases, localized gamma-ray bursts or even X-ray flares can be detected from light years away. These magnetic fields also manipulate interplanetary dust and plasma. Particles traveling through the magnetosphere often become highly charged, altering their trajectories. This can create dense bands of energetic particles that persist for centuries, posing a significant threat to anything attempting to traverse the area. Even robotic probes would find these zones impenetrable without heavy shielding. The structure of these magnetospheres extends far beyond the planet itself. In some cases, their influence reaches hundreds of thousands of kilometers into space, overlapping with the orbits of nearby moons or even neighboring planets. This overlap creates regions of overlapping magnetic chaos, where charged particles are funneled into complex patterns, intensifying the radiation and creating unpredictable energy fields. The magnetospheres of massive gas giants serve as prime examples of these phenomena. Their immense gravitational pull and rapid rotation amplify their magnetic fields, creating radiation belts strong enough to emit detectable radio waves. These natural radio signals are a direct result of the planet's magnetic interactions, and they are so powerful that they can be observed from Earth using radio telescopes. Even smaller planets with unusually strong magnetospheres pose unique challenges. For example, their fields can compress the planetary atmosphere at the poles, concentrating radiation in those areas and creating intense jet streams. This phenomenon alters the planet's climate and makes the polar regions incredibly hazardous. If such a planet were to host a moon within this zone, the effects could be catastrophic. Some exoplanets exhibit magnetospheres strong enough to disrupt nearby stellar activity. By interacting with the star's magnetic field, these planets can trigger localized flares or enhance coronal mass ejections. This interaction turns the planet into a sort of cosmic magnifying glass, amplifying stellar energy and redirecting it back into space. In multi-planet systems, overlapping magnetospheres add another layer of complexity. Planets orbiting close to each other can create regions of intense magnetic interference, where the combined fields generate chaotic radiation zones. These areas are particularly dangerous for any spacecraft attempting to navigate between the planets. There is more at risk for moons in these planetary orbits than just surface bombardment. In the case of moons that undergo magnetic heating, interior friction is caused by a combination of tidal forces and the energy of the magnetosphere. Because of the rapid melting of underlying ice, new seas can form, but they will be promptly destroyed by the high radiation that results from this heating. The visual effects of these magnetospheres are both stunning and deceptive. The plasma rings and auroral displays may seem like natural wonders, but they are harbingers of danger. Observing these phenomena from afar offers a glimpse into the chaos, but approaching them would be a death sentence for any spacecraft or astronaut. One of the most striking effects of extreme magnetospheres is their ability to emit plasma jets. These streams of energized particles are ejected from the planet at high speeds, extending thousands of kilometers into space. These jets create their own radiation zones, compounding the hazards already present within the magnetosphere. While magnetospheres often serve as shields for planets, these extreme examples show how they can also become cosmic hazards. Their ability to trap and accelerate particles turns them into natural accelerators, producing radiation belts and particle streams that are inhospitable to life as we know it. These environments remind us of the delicate balance required for life to thrive. While Earth's magnetosphere protects us from the sun's harmful radiation, the extreme versions found elsewhere in the universe highlight how even a slight deviation in magnetic intensity can turn a protective field into a deadly force. These zones serve as powerful reminders of the fine line between habitability and hostility in the cosmos. Fragmentation zones of giant molecular clouds. The chaotic heart of fragmentation zones in giant molecular clouds is a vivid reminder of how dynamic and hostile star-forming regions can be. These regions, rich in cold molecular gas and dust, are the birthing grounds of stars, but they are far from tranquil. The forces at play here are immense and unforgiving, crafting a stage where violent collapses, intense radiation, and rapid evolution are the norms. Within these dense molecular clouds, small changes in density can tip the scales toward gravitational collapse. When this happens, pockets of gas rapidly contract under their own gravity, leading to the formation of protostars. However, this collapse isn't always smooth. The turbulent motion of gas within the cloud creates shockwaves that can heat surrounding material, amplifying the chaos. These shockwaves act like ripples in a pond, but instead of water, they ripple through cold, dense gas, compressing it and triggering additional collapses in a chain reaction. As new stars ignite, they send out immense bursts of energy in the form of ultraviolet radiation and stellar winds. These emissions carve out bubbles within the cloud, creating zones of ionized gas known as HII regions. These regions expand, destroying nearby molecular material while simultaneously pressurizing the gas around them. The pressure from these expanding bubbles can sometimes trigger the collapse of nearby dense regions, leading to further star formation, a process known as triggered star formation. But the creation of stars is only one side of the story. The aftermath of star formation can be equally violent. Massive stars that form within these zones live short, intense lives, burning through their fuel in just a few million years. When they reach the end of their lifespans, they often explode as supernovae. The resulting shock waves from these explosions ripple through the cloud, compressing some areas while dispersing others. In some cases, the shock waves create high-pressure regions that kickstart new waves of star formation. In others, they simply blow apart sections of the cloud, dispersing the raw material needed for future stars. The density of these regions often leads to the formation of tightly packed stellar clusters. Within these clusters, gravitational interactions between stars are common. Close encounters between stars can fling them out of the cluster entirely, creating rogue stars that wander through the galaxy. In other cases, these interactions can lead to the merging of stars, forming even more massive and unstable objects. These mergers often result in stars with short, chaotic lives, ending in dramatic supernovae, or even direct collapses into black holes. Amid this chaos, the magnetic fields within these clouds play a crucial role. These fields thread through the gas and dust, influencing the way material collapses to form stars. However, the intense activity within the cloud often distorts these fields, creating irregularities that further destabilize the environment. This interplay between gravity, turbulence, and magnetic forces ensures that no two regions of a molecular cloud evolve in the same way. Adding to the complexity are the protostellar jets that erupt from young stars. As material falls onto a forming star, some of it is ejected along the star's magnetic poles at high speeds. These jets, composed of gas and particles, can stretch for light years, cutting through the surrounding molecular cloud like cosmic blades. Wherever they go, they disrupt the local environment, carving out channels and dispersing material. Occasionally, huge parts of the cloud break apart into smaller clusters due to the extremely harsh circumstances within these zones. These clusters have two possible outcomes. They may either collapse into stars, or they can stay as gas pockets and gradually disperse. There is a fine balancing act between the forces that pull and push the material in different directions throughout the fragmentation process. Whether a certain area turns into a thriving nursery or a desolate wasteland is decided by the result of this tug-of-war. The presence of massive stars within these zones adds another layer of complexity. These stars emit intense ultraviolet and X-ray radiation, which ionizes the surrounding gas and makes the environment even more inhospitable. This radiation not only heats the gas, but also drives chemical reactions that can alter the composition of the molecular cloud. For instance, molecules like carbon monoxide and ammonia, which are common in these clouds, can be broken apart by the radiation, limiting the range of chemical processes that can occur. Despite the chaos, these regions are also sites of incredible creativity. The formation of protoplanetary disks around young stars is a testament to the transformative power of these zones. These disks, composed of gas and dust, are the precursors to planetary systems. However, the same forces that drive star formation can also disrupt these disks. Nearby supernovae, stellar winds, or close encounters with other stars can strip material from these disks, leaving behind incomplete systems or scattering potential planets into interstellar space. When cloud material gets too thick in some places, it produces formations called Bok globules. In order to protect their contents from the strong radiation and turbulence of the larger molecular cloud, these little black clouds are segregated from their surroundings. Stellar creation can occur slowly and steadily within these globules because of the generally more stable circumstances there. But the bigger forces are still at work, even in these isolated areas. A Bok globule can have its contents scattered and star formation halted if it is disrupted by an incoming shockwave or by the effect of a neighboring giant star. The interplay between these forces ensures that fragmentation zones are among the most dynamic and deadly places in the universe. The intense radiation, gravitational collapses, and violent feedback processes create an environment where survival is nearly impossible. Yet, it is within this chaos that the seeds of new stars and potentially new planets are sown. These regions are both destructive and generative, embodying the dual nature of the cosmos, as the raw materials of the universe are forged, scattered, and reassembled. Sizzling ionization fronts. Ionization fronts are evidence of the tremendous force of radiation in the enormous cosmic landscape, where extraordinary events mold the cosmos. In these regions, neutral hydrogen gas is hit by ionizing ultraviolet radiation from large stars, creating a sea of ionized particles. Chaos is reshaping the interstellar medium as a result of energy and matter interacting in these areas. The energy pouring from massive stars drives the ionization process, creating regions of intense turbulence. The boundaries between ionized and neutral gas become volatile zones where shock waves ripple through space, compressing and heating the surrounding medium. These supersonic expansions leave their mark, creating intricate patterns in the gas and dust, sculpting pillars, ridges, and other structures that stand as monuments to the force of stellar radiation. These fronts are not just chaotic, they are transformative. As the shock waves move outward, they compress nearby gas clouds, triggering the collapse of dense regions. This process, paradoxically, gives rise to new stars. While ionization fronts destroy molecular structures and strip away dust, they also act as catalysts for star formation, making them a double-edged sword in the universe's cycle of creation and destruction. Evaporating gaseous globules, or EGs, are small, dense regions caught in this turmoil. As the radiation exposes and erodes these globules, their dense cores can survive long enough to form stars. Yet, the relentless ultraviolet photons ensure that much of the surrounding material is vaporized, leaving behind isolated stellar remnants. These interactions highlight the delicate balance between creation and annihilation at ionization fronts. The high-energy environment of ionization fronts is lethal. Ultraviolet photons disrupt molecular bonds, destroy organic compounds, and obliterate dust grains. This process sterilizes vast areas near massive stars, making them inhospitable to life as we know it. Even the most resilient molecules cannot withstand the destructive reach of this radiation, turning these zones into cosmic deserts. The pressure from the intense radiation pushes outward, creating expanding bubbles of ionized gas. These structures, often observable as glowing H2 regions, mark the boundaries of stellar influence. Within these bubbles, the interplay of pressure and temperature creates zones of extreme instability. Radiation-driven winds amplify the chaos, accelerating gas and dust to supersonic speeds. These winds carve through the interstellar medium, creating dynamic and rapidly evolving structures. Shock waves at ionization fronts generate further disruptions. Neutral gas caught in their path is compressed and heated, forming additional shock layers that spread outward. The turbulence in these zones makes them hotbeds of chemical reactions, altering the composition of the surrounding medium. Complex molecules can form under these conditions, adding to the intricate tapestry of interstellar chemistry. Bow shocks emerge when stars move through ionization fronts. These curved shock regions are created by the interaction of stellar winds and radiation with the surrounding gas. The energy concentrated in these bow shocks makes them some of the most dynamic and violent features of ionization fronts. They reveal the power of the stars driving the ionization process and offer insights into the forces shaping the interstellar medium. Time is a critical factor in the evolution of these regions. The lifespan of ionization fronts is tied to the lifetimes of the stars fueling them. Massive stars burn brightly, but briefly, and as they die, the radiation driving the ionization ceases. The fronts collapse, leaving behind remnants that tell the story of their violent existence. Reflection nebulae, glowing clouds of gas and dust, often mark these remnants, scattering starlight and providing a haunting after-image of the once dominant stars. Feedback from ionization fronts plays a significant role in galactic evolution. On a larger scale, these regions shape the distribution of gas and influence star formation across galaxies. The radiation and winds from massive stars can drive gas out of galactic disks, creating galactic fountains or winds that transport material into the intergalactic medium. These processes regulate the availability of gas for future star formation and affect the overall structure of galaxies. The role of ionization fronts in regulating stellar nurseries is equally significant. Young star clusters embedded within these regions experience intense heating and pressure. The radiation erodes the surrounding gas, exposing protostars and accelerating their evolution. However, the destructive power of the radiation often disrupts the formation of additional stars, limiting the efficiency of stellar nurseries. Interactions between cosmic rays and ionization fronts further complicate matters. Interactions between ionized gas and cosmic rays, which are high-energy particles in space, change the gas's characteristics and trigger other chemical processes. The region's energy can be amplified by these interactions, leading to the formation of ionization front hotspots. Patterns of infrared and X-ray emissions from ionization fronts provide valuable insights into their dynamics. These regions emit strongly in these wavelengths, revealing the temperature and composition of the gas. Observations of these emissions allow astronomers to map the structures of ionization fronts and understand the processes driving their evolution. Radiation can reach deeper levels inside molecular clouds as these fronts slice through the interstellar medium, forming pathways of ionized gas. These channels change the terrain of star-forming regions by exposing dense gas areas to the destructive impact of ultraviolet radiation. The construction of these ionized passages emphasizes the extensive impact that ionization fronts have on their environments. The temporary nature of ionization fronts adds to their intrigue. These regions are fleeting phenomena in the grand timeline of the universe. They arise quickly, evolve rapidly, and dissipate as their driving stars die. The remnants they leave behind are reminders of the stars that once dominated their regions, offering a glimpse into the life cycles of the most massive stars in the cosmos. At the edges of these fronts, dense filaments of gas and dust form, creating intricate structures that highlight the interplay of forces at work. These filaments are shaped by the combined effects of radiation, shock waves, and turbulence. They stand as testaments to the power and beauty of the processes that govern ionization fronts. The interplay of forces within ionization fronts showcases the balance of creation and destruction that defines the universe. These regions are not merely zones of chaos, they are laboratories of cosmic evolution, where the seeds of future stars are sown amidst the ruins of the present. By studying these fronts, we gain insight into the forces that shape galaxies, fuel star formation, and drive the cycles of matter and energy that define the cosmos. Through their dynamic nature, ionization fronts reveal the intricate and interconnected processes that govern the universe. As we venture through the most dangerous corners of the universe, we're reminded of how fragile and unique our existence is. From the searing devastation of Blazar jet impact zones to the relentless gravitational chaos of supermassive binary black holes. These deadly locations reveal the raw power of the cosmos. The Pulsar wind nebulae churn with high-energy storms, while Quark star surfaces present a reality where matter itself is unrecognizable. These places, though inhospitable, are a testament to the extremes of creation and destruction in the universe. They challenge our understanding and ignite curiosity, leaving us in awe of a universe that is equal parts breathtaking and lethal. Make sure to subscribe to the channel if you enjoyed the video. Thanks for watching.